And that is true for metals, ceramics, mills, basically most of the crystalline materials that we use as engineering components. So what we want to see is basically material structure, and we want to see it with the real space, like grain shapes or crystal shapes, and we also want to get internal orientation and strain information. So for that, diffraction imaging is the way to go, or one of the ways to go. And we want to, as I said, we want to have a multi-scale imaging. So we want to use millimetric samples where we have the bulk conditions, having grain sizes, on the order of a couple of hundreds of nanometers up to hundreds of microns if you want. And we want to have some resolution that actually can do a zoom in and out kind of analysis. So for that, we need to have a method that sits between these 3D XRD, diffraction contrast tomography, or the coherent imaging method, somewhere between linking this gap. And also we want to study dynamics because if you want to improve some materials, we need to look at in situ, in operandi conditions. And for that, we need to have a full field imaging so that we can do a fast mapping of a given volume, and without damaging the sample in terms of irradiation when you're doing in scanning methods. So taking all this into account, we found our dark field microscopy and also bright field X-ray microscopy somewhere sitting in between in this temporal and spatial resolution plot, having information from material structure with dynamics and a multi-scale approach. So basically how this works is that you take a sample, either polycrystalline or a single crystal, and this sample can be millimeter size depending on the the absorption of the X-rays. So we basically use typically from 10 to 35 kiloelectron volts. So depending on material, you can have rather 2-3 millimeter samples, depending on what energy you're at. Anyway, so what we use is basically an X-ray objective lens, but just like in bright field X-ray microscopy, where you have absorption and phase contrast in the magnified image, we basically have a diffracting element of a given HKL, and we then focus that beam onto a detector that's located about 5 meters away from the sample. And then what we see is basically the image of the diffracting the volume, in this case, for example, a grain from a polycrystalline sample. And then we have these sample tilts and 2 theta, so we can map the strain and orientation with spatial resolution around 100 nanometers. Can go down a little bit for extreme cases, but that's most of the time what we use for the time being. Very high strain resolution, better than anything on the market for the moment. Temporal resolution keeps going down. And as I said, sample size like this. So this is basically this dark field microscopy really influenced from the dark field TEM. So it's only making natural sense just to compare the 2 techniques. So basically, if you take dark field microscopy, spatial resolution is definitely way worse than TEM. But on the other hand, we don't really have the sample preparation issues where you have 100 to 200 nanometer thick thin films, polishing damages and free surfaces. So it's not really bulk. And compared to TEM, the strain resolution is way better thanks to the compound reflective lenses that we use as objective lenses. And of course, since that the whole thing is not in vacuum, that we can put all sorts of sample environments to study in situ evolution of different systems. So rock and roll imaging, what I said in the beginning, is basically we have a couple of sample tilts and the 2 theta arm here. And one of the main scans that we have, what we call the mosaicity scans, is basically like an EBSD scan, but around the given Q scattering vector. And we scan the local orientation, if you want, local pole figure around a given Q by rotating the 2 sample tilts. And then we can map these recorded images. We can combine them together and then make a orientation map similar to the strain that we could do while moving the lens and the detector arm, or we can combine these two to get 3D orientation space. Right. So some of the cases basically, well, mostly we focus at ID6 mostly on metallurgy and functional materials, but also we have semiconductor studies and some biominerals. And of course, I cannot show all of these results or all of these examples in this talk, but I'm going to pick some of those and hopefully see some cool results, what you can do using this dark field microscopy technique. So the first part is basically what I've been focusing on for the last 4 or 5 years, mostly on metallurgy. And I'm going to show you some examples on deformed metals and their annealing. So to put things in context, maybe you're not really familiar. When you're producing a metal, it really undergoes a lot of thermomechanical treatments, using which you can actually control the properties of the material. And from this, you deform, like cold deformation, hot deformation, you increase the stored energy, and then you re-anneal. From the stored energy, you recrystallize your system, and then you have grain boundary motion. You may have different alloying elements that may do segregation, changing the properties, also depending on how you deform or what kind of sample you have, what kind of material you have. You may have different grain texture, and this affects the properties. So there are a lot going on in this. So we need to understand the deformation microstructures, annealing microstructures in depth. One of the main challenges over the last years is basically to probe the deformed state of metals. So deformation, I'm talking about cold rolling, hot rolling, forging, that kind of deformation that can go up to strains 2, 3, 4, 5 true strain, engineering strain, von Mises if you want. So we have this high energy diffraction microscope, or the other names, 3D XRD or a similar method, diffraction contrast tomography. These methods provide grain filling maps from volumes of metals and orientations and strain, very powerful techniques. But because of peak overlapping issues from the diffraction spots, these techniques cannot really go beyond 20–30% deformation. It becomes really hard to generate maps, basically index these diffraction spots. We also have different diffraction techniques, synchrotron-based techniques like differential aperture X-ray microscope, and you can go beyond these deformation levels. On the other hand, the spatial resolution is on the order of 1.52 microns. So the cell sizes, the more you deform, they become smaller. So you need to have at least a better spatial resolution compared to the cell sizes. Of course, the industrial standard is for the last 20 years is EBSD, electron backscatter diffraction, and of course TM is very important since many years. But again, these are generally surface-based methods, even though you can do 3D EBSD, but then you're actually sectioning the sample, so you're destroying the evidence. So it's very hard to study in situ from bulk in these techniques. So if we sum up, basically, we have all these methods, but we either don't have bulk sensitivity, deformation levels cannot go, and resolution is not good enough for the cell sizes. So the larger deformation levels with high spatial and angular resolution in industrial level and structures is challenging. So what I'm going to show you here is basically a first of its kind study on a cold rolled iron alloy, basically iron silicon alloy mostly. So you can think about a ferritic steel if you want, or interstitial free steel. In this case, it was a generic alloy. And this is the EBSD structure that you can see. You have these cold rolled structures, the elongated grains with shear and deformation bands for different orientations. And what we did, we were able to map this one of the elongated grains from a sample within the bulk in 3D using dark field X-ray microscopy. And also by placing a 2D detector, we can also have a look at the volumetric evolution of all grains, not only one grain, because using dark field microscopy, we have this objective that filters out all the other diffraction elements. So we actually focus on one single orientation place within 10 degrees or so. So that means one grain or a couple of grains at once. So here is the image of one grain from the dark field microscopy study we did. And you can see this with about 140 nanometer resolution. And you can see these orientation gradients because of deformation. The rolling direction is in this direction here. you can see deformation bands, and this is from the high stored energy regions of this sample. So what I mean by that is basically, if you're familiar with this kind of Euler plots from the orientation space, you basically have different texture components, and these components carry different stored energies. So when you anneal one of these deformed samples, you basically produce recrystallization faster most of the time from these stored energies regions. So our grain, our snake, let's say, was from this region. What we found, I'm going to show you how we found this from the same sample using texture analysis as well. So before going into what happens when you anneal this sample, so when you heat the sample, I just want to show different components of orientation. So two sample tilts orthogonal to one another, you can really see the contributions of deformation gradients in orientation, but also deformation lines that are deformation bands, basically, that are very generic, that we can find from EBST and TEM structures. But this is one grain and its section from the middle of the sample. So there's no surface. So this is one of the section of the sample. And you can also do a strain scan and get the actual strain and relative strain around these points. And you can get the strain stored energy. And what you can see, we have these higher strain points around these deformation bands, which are very important to locate because this is where you normally expect to have the recrystallization. One of the main problems in metallurgy or material science nowadays, is having for a long time, is how we can really choose or locate where the exact nucleation sites will be from deformation state. So this is a very important point towards that direction here. So what happens when we anneal this for about 10% recrystallization, we have all these new guys appearing, very fine structure, almost dislocation free. And we still have the deformed structure. So we can really see the link between the remnant deformed structure, but also the new grains nucleating from the junction points and the grain boundaries from the deformed structure. So this is very important to understand the orientation relationships between the deformed parent matrix, if you want, and the new grains. And if you anneal further, you will have grain growth, and you will see a competition between different grains. For example, this guy will grow, and this one as well, while eating the other ones. And you can really see how they grow and which orientations grow, which orientations don't, from the 3D structure. And you can make some statistics, although there's not so many grains for this study. It was just a proof of concept study here. We can really see there's a side-dependent growth as a function of annealing time. Furthermore, you can actually get some geometrically necessary dislocation density from the orientation scans, similar to what you can get from kernel average misorientation plots of EBST. What you can see in the beginning, we have used the stored energy quite a lot. And then since the stored energy left with the early recrystallization, then we have a rather slower decrement of the dislocation density as we continue heating at a constant temperature. So to sum up, we basically have all these layers. So this is just different layers of the 3D structure. You can see what happens at 80 seconds. And then the more you anneal, you get these grains getting bigger and all these grains popping around in orientation space around the main deformed grain. At the same time, of course, there are other grains here. So this is the deformed structure X-ray diffraction image of the 360 rotation. You can see the different Bragg peaks. And what you see here, this is coming from 500 by 500 micron slits opening. So it's most of the sample, many grains here. And the more you heat, you can see the texture does not really change around it, but you have seen the recrystallized grains appearing as bright spots here. And what you can do, you can basically do a texture analysis and see how these evolve and compare it with the EBST. You can see a relatively good match or very good match if you want. And then you can study all the grains, how they, from the same sample without dismounting the sample, how they actually change. And you can see the texture index actually increases in the first place where we expected all that little grains around the deformed grain because they have similar orientation to the deformed structure. So they contribute to the overall texture. and then the other grains from the least stored energy regions nucleate, and then the overall texture becomes more homogeneous. So for this study, this was one of the first study to show 3D structure of the 85% deformed ferritic alloy, and we showed the link between higher misorientation zones coming from higher strained grain boundaries and junction points. These are the preferential nucleation sites. This is very important for crystal plasticity modeling. You can use these things for input and also for grain growth as for phase field modeling. So the FXM shows here as a powerful tool to capture all these things. So these results that I've shown was done from an experiment late 2018, which was before the ESRF upgrade to extreme brilliance source. So now we have, since 2020, we have brighter light. So that means faster experiments. Of course, it comes with its own problem like data storage and some unwanted coherence for some cases, not for all. But all the results I'm going to show you now is going to be from 2020 and onwards. So here's a study from our colleagues from Purdue University, especially run by Sven Gustafsson and Mike Sangrit. So what they wanted to do, they wanted to combine diffraction contrast tomography with dark field microscopy, because one of the main downsides of dark field microscopy is that you don't have neighboring grain information, so you cannot really fill the whole orientation space. Whereas for DCT or HEDM, you can have all these. So what we did, we basically got this construction and found one grain from that sample and then scan it with 120 nanometer resolution almost using dark field microscopy. So when you're doing that, you're able to separate different slices from the 3D like this from a grain, and then you can really locate what parts are more strained, what parts are more in damage because of the fatigue loading here, in this case for this alloy. And you can actually put this into context and see grain boundary junction points have higher strains in 3D, which you cannot really get with DCT in this strain and spatial resolution. But using DCT, you can actually locate where the grain is and what the shapes of the other grains around this grain is. So it's a very powerful demonstration of using a multi-scale approach here. And I'm going to talk more about this at the end, but very powerful study here that can show a bigger context within samples like this. Another study that we've been doing lately is on additive manufacturing, of course, a very hot topic. So this is a nickel superalloy. This study is under preparation. So what we want to do is basically wanted to test and see how the effect of surface, first of all, in EBSD analysis affects the results, like polishing damages and free surfaces. What's the effect on and the surface methods like EBSD on orientation and strain? So we use this same sample that we used in EBSD, and we look at with a 1D focus beam. Then we move the sample in Z direction so that we get the thickness as it moves down to the samples inside. So this is a micrograph orientation scan that we had with the dark field microscopy. You can see different orientations for each pass of this additive manufacturing. Because of high cooling, you can see dendritic structures almost with different orientations at each pass, and the overall orientation spread around 1.2 degrees. And this is the EBSD micrograph of the same grain here. And this is the 3D structure that we get from dark field microscopy scans. So what's interesting here is using the same sample, you basically have this strain spread increase that is going down as we move towards the interior of the material. And about 10 micron size here is about damages from the polishing. But this is really where you're scanning with EBSD. So one must be really careful in talking about what the measured orientation and strain, that it is really relative. And actually, if you go down into the bulk, there's more interaction between different grains and less surface effects from the polishing. And you can really see this nice relative strain distribution pretty high value because of the high cooling rates you can have captured by dark field microscopy. This study is under preparation here, is hoping to have it come out soon. And another thing, what we can get if we do this 3D scanning, we can basically have an idea about how heterogeneous is this structure as we go down. So each step here is 3 microns from the surface, and you can see the orientation is completely different as you move inside the sample. So these are very important things to understand to design better materials and change the processes of cooling and additive manufacturing. How am I doing with time? How much time do I have?
You have, I think, 10 minutes or 9 minutes.
All right, cool. So I'm going to just show this fast again. So a combination of EBSD and dark field microscopy here. This is another study on power electronics. And you have these copper chips in these electronics. And one of the main issues is basically the thermal fatigue. So you have thousands of cycles in these materials, heating and cooling. So as a function of that, at some point you start having these deterioration coming from the grain boundaries. This is a CM picture, and you can see the voiding occurring from the grain junction points. And what we wanted to study, we basically wanted to study intragranular effects on one grain for different thermal cycles. So here's an EBSD structure. We wanted to focus on this very grain. And in this case, we basically did the dark field microscopy first, and then did the EBSD. So all the dark field images here do not really have any polishing damages compared to the EBSD studies here and compared to the study that I've just shown. So basically using the same approach here, we look at this 111 peak of a given grain from different samples with different thermal cycles, and we scan their orientation and strain. So here's one grain. We have all these twin boundaries, annealing twins basically in copper, and you can see the misorientation map increases around the annealing. Just have a look at these numbers here. These numbers are pretty small, and generally what you have for EBSD, you get this as single colors in orientation. Of course, the high angular sensitivity of the dark field X-ray microscope method here, you can see all these intricate details about orientation within a given grain and strain as well. And you can see strain increases around these boundaries and grain boundaries as well. So here's another grain from a thermally cycled sample. You can see the strain values are much higher compared to this big grain. And this another grain again from a cycled sample, again higher. So if you want to really compare these as deposited grain with the 50K cycled grains, you can see this strain comparison in histogram here. This is completely different. So the conclusion is basically thermomechanical treatment results in this plastic strain accumulation in the grain boundaries and having cracking. And this is because of the near boundaries, and this is driven by the copper diffusion during this thermal cycling. Right, so last but not least, I'm going to show just a little bit of single crystal studies that we had. This study was led by our colleague, Professor Leora Dressel-Mary. This is an aluminum single crystal about a millimeter thick, and we have this nice optical furnace in our beamline, which can go up to high temperatures and have a very nice thermal stability without touching the sample. So what we wanted to study is basically study the dislocation dynamics in real time as we get close to the melting point, really close to the melting point. And you can see these different breathing motion happening when you're getting closer, and then interactions between different dislocations happens. And then we start having a flow because of higher temperatures. So we have different dislocation characteristics at different regimes. So what we concluded, basically, we have these stabilizing forces at some point for dislocations to get to place. But as we come really close to the melting point, thermal effects really dominate. So this is a very nice piece of work if you want to check this out. This is on Science Advances. This is one of the first demonstrations of dislocation motion in 3D in real time. Right. So last but not least here, this is another study that was actually inspired by this. So we said, all right, instead of doing this in situ on a given layer from the 3D, what if we just actually anneal a single crystal for about 10 hours close to the melting point and just study the dislocation boundaries? So using an incident beam like this with a sheet form with about 600 nanometer size, and scan the sample all the way and get about 400 micron microns cube volume here. So using the weak beam contrast from rocking curve basically being in the tails, we can get the information from these locations. And this is a video when you move the sample in vertical direction and see all these dislocations popping up. So if you actually reconstruct all these, what you find is this amazing picture that dislocations actually form boundaries that extend way beyond what we can see with TEM, just because you have thin foils. Even if you have tomography, you won't go beyond 500 nanometers. So what we also found, all these boundaries are actually corresponding to known crystallographic directions. So it's a study that you can reach on preprint. It's under review nowadays. Hopefully it will come out soon. And with this, I'm just going to sum up that I hope I have convinced you that dark field microscopy is a cool diffraction-based imaging technique, complementary to different techniques from both synchrotron world and electron microscopy techniques. And what we have we have polycrystallines or single crystal. If your material is crystalline, we probably can look at it depending on the feature size. Before I close, I want to just give you two little information on what's going to happen to the current ID6. So within the framework of 4 flagship beamlines at the SRF with the EBS upgrade, ID6 will be going to moving on to ID3. And now we're going to have the last experiment next 2 weeks, and then we will move the whole bench to the new beamline. And we will have users for early 2024. So if you want to apply for a proposal, please contact me. And the deadline will be September 2023. And what we're going to have in the new beamlines, basically improved mechanical thermal stability, basically will help for higher spatial resolution, of course, with the improvement in the X-ray optics. We will have a new goniometer where we can actually do all these 3D XRD DCT versus dark field microscopy multi-scale imaging. And also, we will have a pink beam operation where we can do dynamic studies, faster acquisition, and for hybrid structures. Of course, we will have unshared sources, because now we're sharing with a different beamline, the same optic site. So we're going to have a proper beamline now. And with that, I'd like to thank all these people that contributed to this work, especially Carson Detlefs, Phil Cook, Henning Poulsen, and Hugh Simons here, and all these other important people. Of course, I'm not going to go through all. And please feel free to send me a line if you want. And thank you for your attention here. Thanks a lot.
Thank you. Any questions for the speaker? Are there any questions in the chat? I thought I saw one earlier.
So there's some questions
I guess
here.
that was a.
Can this technique,
to the previous talk? Sorry.
Can this technique, can we use it for geopolymer materials? I'm not familiar with geopolymer materials, but as I said, if it's crystal and if it has feature size about 200 nanometers, yes, we can. There's another question by Kuda. Amorphous state to estimate amount of crystalline. I think we can. Yes, we can discuss that over coffee or something. Yeah, I don't see any other question.
You can put your questions in the chat. So we're running a little bit behind schedule, but I want the speakers to give their talks in their totality, and we would just have a little shorter tea. So I apologize. I actually am a very bad session chair because I lose track of time because I get engrossed in the talk. Anyway, Julio is here and is ready to give his talk. So, okay, yep, you stop sharing your screen and we can move on. Thank you.
Okay, now can you hear me? You see my screen?
Yes.
Okay, so thank you very much for the introduction. Thank you very much for the opportunity to be here to present my work. It's a great pleasure to be in this community, helping as much as I can. So today I'm going to talk about quantitative and chemical nanoimaging of heterogeneous materials by this.
Can you go to I'm sorry, can you go to presentation mode on your?
Yeah, because I have the bar on the top. Okay. So I'm going to do this by showing this technique with this funny name called 3D X-ray tachograph. I'm Júlio César da Silva. I'm from Grenoble. So, but before starting, I would like to touch a topic that I think that everybody knows is how cook. You have the ingredients for your cooking, very homogeneous, each one of them with different properties, and you put all together in a recipe with a protocol to get a result. If you mess up the protocol, you don't get the good result. If you miss an ingredient, it doesn't taste good, your cake, right? And what you get at the end, if you do properly, is a good chocolate cake, which basically is a scaling up manufacturing process. You see that your cake does not have the same taste, does not have the same properties or the same structure as your initial material. So when you talk about heterogeneous material, I'm talking about this kind of materials that are built for homogeneous materials or crystalline materials or whatever, and then becomes amorphous or whatever with different properties that have the properties that we want. So this is exactly what happened, for example, in the oil industry. This is the scale up process of catalysis for oil refinery. We start for very small, from very small materials, crystalline materials that optimize a lot, but those small materials cannot react properly in a higher scale that we call the technical scale in a reactor, which have meters, 10 meters, 20 meters high or large. So you need to scale up, start from the active site for a agglomerate, a particle, a powder. And when you have the powder, you have the structure that acts as catalyst there, but it needs to support harsh condition of temperature, pressure, a long time of operation in this reactor. So you need to structure these powders in a way that the shape is well compact or in the way that we want in the reactor. And you need to add additives to control the temperature, to not destroy the material. And you do this, and you go to the plant, test, and if it's not good, you come back and optimize again the primary screen, go to secondary screen, scale up, and this costs money. And if this is not well done, at the end, you have your product that is not fully operational or have a short time of life, and then you need to replace them. And that, again, is costs money. So you need to really think how to optimize the system. So basically, you are cooking your system. You need to put your catalyst, for example, in this case, a zeolite, with peptizer, binder, plasticizer, lubrificant, with good temperature. Up to date, it was done more or less empirical, but since recently we start to systemize or to give a systematic way to analyze this kind of materials. And just to give an idea of the shapes that they use, you can see here some pictures. They can be as big as a small cat, or it can be as small as a very, very tiny dust powder. So how these materials work? I chose one, which is the fluid catalytic cracking catalyst. It's one of the most important catalysts to transform oil, crude oil, to gasoline or other fractions that are important for us. And they are porous inside. So when they enter in the reactor, they are beautiful, round spheres of about 100 microns, very porous. The surface is smooth. And then during the operation, it enters in the reactor, goes to the regenerator, goes back to the reactor, and this takes years sometimes. And then at the middle of the life, we start seeing some changes in the structure of the material. And at the end of the life, you see that you have even nodules that forms around this material, completely blocking the access of the reactants to the pore structure where the zeolite and the active sites of catalysis are. So you see that if you have a macropore that is blocked, it never gets to the catalyst. So the catalyst is deactivated, no matter how good this catalyst to us. And if you block the micropores, it's the same. You may have some fraction that gets already cracked, but not the end. Basically, it's like this cartoon from Professor Javier Perez Ramirez, where you see the reactants entering in the mesopores highways, and you see some active sites where some of them are very active, some of them are already dead, some of them refuse to work. And so it shows that this procedure is not 100% efficient. Basically, today we're like 30% is already very good. And see, then you get your products. And then to try to optimize this structure, what we did, we took this material, went to the beamline, we did this tachographic X-ray computed tomograph, which is basically a combination of tomography and tachograph for 3D imaging. We scan each bead, and here I show some cuts around the particles, and you see like the pristine size, the structure is more or less the same everywhere. In the middle life, we start seeing already the formation of some eutectic phase, amorpho layer that blocks the porosity, but you still have access to there. But at the end of the life, you see these nodules, they are high density, they are amorphous, and they are completely blocking the access to the pores. So all the things trapped inside of the pores cannot go out, and nothing new can go in. And you can even see here some carbon deposition, what we call coke. And this, since the technique is quantitative, we can identify where the zeolite is, where the clay is, where the porosity is, and this layer. And clear see here the layer going around the particle, blocking the access of the porosity. So the company needs to remove this catalysis and put new one. So it takes money because you cannot do anything with this dead catalyst. So this I showed what I did with tachography, but I anticipate the results before showing the technique. But to understand the technique, first we need to understand how you can do this using coherent waves. Any light can be coherent at certain extent, but of course you want to get the maximum of coherent as possible. And those decks will show you how to do, because a perfect source, coherent source, is a point. But you never have a point. You have always an extension, and each point of this extension may be a source. So if you look at these decks, they drop in the water, and as soon as they drop in they jump in the water, you see the waves that get propagated from them, completely random. You look at this is completely incoherent. But if you wait long enough and look farther, you start seeing that the waves, they start to organize back again. And as you see in this picture here, after 1 minute, you have perfect plane waves there, a perfect coherent waves. And this is the principle of von Zernick theorem. It means that if you don't have a point source, but if you can look to this source from a very far distance, very far away, you can consider this source as a point. And this is exactly why you need long beam lines for coherent imaging. But you may have a little bit of coherence also from the sunlight, from the stars, or because they are very far away. But for synchrotrons, you need long beam lines because of this effect. When you get coherent beams, they look like as the ones here below. The colors have nothing to do with the frequencies. You see that if it's not monochromatic, it cannot be fully coherent. It hardly to get some correlation there. Monochromaticity helps, but it's not 100% efficient. You need like high monochromaticity and correlation between the phases. Somehow that if something happens with the blue wave, the pink wave will know, the green wave will know. It means that if you put an object that has this refractive index that you may know from X-rays that it's complexity valued, one part of the beam is hitting the object, the other part is not. It's more or less like if I'm sending my soldiers to the battlefield. Some of the soldiers will not go through. That is when beta is very important, and they will be absorbed. They will not arrive to the detector. But if delta, is important, it's more or less like if the soldiers will get only delay, but they will arrive. So you have dead soldiers and soldier delays. But since in X-rays you have 1 minus delta, it's funny because X-rays will advance the phase. It's more or less like if the soldiers were arriving faster than the others that are not injured. So with this phenomenon, you have refraction. Refraction is the deviation of the light, and because of the coherent, you have diffraction. Diffraction is like any light gets interfered by deviation from your path. Bragg diffraction of crystal is only a special case of this situation, okay? So you have the Fresnel diffraction, you have also what's called Fraunhofer diffraction, depending where you put your the sample and your detector, of course, in a transmission geometry. If you put very close to the beam, the waves, they don't have time to interfere. So you only have absorption contrast. If you put a little bit farther, you start having interference, not that much, but you start seeing soft matter, you start seeing tissues or things that would have not much absorption. And if you go a little bit farther, you start seeing the image of your sample, but with a little bit of fringes around, what you call the Fresnel fringes. And this is the holographic regime. But if you put it very far away, the interference is so important that what you see is not the picture of your sample, but an interference pattern that we call the speckle. Is a diffraction pattern, but without crystal. And this diffraction pattern is related to the Fourier transform of the object. So I'm going to start talking about this, and then I go to the near field regime. And the far field, these speckles have a function, because if you have an object like these beads, and the coherent length, the coherence of your beam, the distance of correlation of your beam is not so big, what you get is a small angle scattering experiment. We have the firm factor of these beads in there. But if your coherence now is larger than the sample, you still have the form factors, but on the top of these, you have a texture that we call the speckles. And these speckles will retain the information about the whole structure of the sample, because if you look at the angular aperture of these speckles, it's directly proportional to lambda divided by the size of the object. Knowing this, what we do in tachograph is that we do exactly this, but in a scanning mode. We localize the beam in a space. For each position beam, you get a diffraction pattern. So the resolution is not given by the beam size, but the maximum scattering angle where you can still get the speckles. And we scan the sample in a funny shape, keeping some overlapping between the different positions of the scan. And then by doing this, you can recover something that you lost, which was the phase here, because you can only get the intensity, by an iterative reconstruction algorithm where you cycle between the reciprocals, the real space where the image, and the diffraction pattern, because you know they are related by Fourier transforms and inverse Fourier transform. And you do this spot by spot. And on the top of this, you have like this redundancy area, because there are some overlapping, so they need to agree. And on the top of this, the beam is the same for all of them. Because of all of this, you can get not only the amplitude of the image, the amplitude image and the phase contrast image. The amplitude is the absorption, and the phase is the phase contrast image. But you can also get the probe, the amplitude, and the phase. So for the same experiment, you get 4 information. This is 2D. Now, if you transfer this to a tomograph experiment, like a medical scanner, by rotating the sample and at each angle you do a tachograph experiment, you can get a complete 3D map of the refractive index of your sample. You get delta and beta and 3D, and they're fully quantitative. Okay, here I put the open source library that we use in Python, and you can do like things like that. Here I only have the like transverse cuts from the absorption volume and the phase contrast volume here of the cement. This is the ordinary cement, basic alite or thick calcium silicate that is hydrated in a capillary of about 100 microns, and you have a calcium hydroxide and calcium silicate hydrated. But you have this Y, the stoichiometry that you cannot know in advance, and you don't know exactly. The only thing you know is like the shapes, more or less, of the phases and the density. So what we do, we segment each phase, calculate their density from the phase contrast, because you can get this, and you see the density corresponds quite well to the expected one. And by using the absorption and the phase, you can combine both in the mass attenuation coefficient. They get the value of Y for the cement. So we got 5.2 plus or minus 0.4. And from bulk measurements in sacks, what they got, it was 5. So we are very close. But the point is that I'm comparing bulk measurement with imaging. So I have an image, I can do this pixel by pixel or voxel by voxel. So I segment my phase, I take the calcium silicate hydrated, and I do this voxel by voxel. I see the distribution of the water inside, and you see these values in color is the value of Y. And you see that by capillary effects, you have more water in the border than in the center. But this is nice because you can go inside the matter and see it. So this is just a video to see that we really have the 3D, but don't lose time on this. And another thing that we really observed is that if you hydrate too much the particles, you have a bump, like the particles get denser in the border. If this like from the border to the inner part, then in the inner part here, then you have the unhydrated part, which does not happen in the unhydrated particles or partially hydrated particles. This was not foreseen by the mathematical models of cement hydration. So it really opened a new idea, a new vision of the cement, and you clearly see this in the image because you see the borders are brighter than the inner part. And if you translate this to water content, you see that you have less water in the border than the inner part. So you think that the particles, as soon as they get hydrated, the products are pushed or are expelled outwards, and they accumulate in the border, and the water can penetrate. You're going to see this later when I come back to another measurement, but this is what you can do, quantitative and chemical. But how about the near field regime? Well, absorption phase contrast, I'm still missing some ideas. Nobody's working on this for a tachograph, but in inline holography, yes, this regime we are doing. And what we do here is that holograph has fringes around the sample, but the beams are never perfect. They are always structured because plane waves does not exist in X-rays, especially when they are coherent. So what we do, we modulate even more this beam or destroy the quality of the beam statically, and you see that we get even more fringes, but you get no information about the object. But if you think that in a plane waves, you move your object laterally on the plane waves, there's no change of the direction of the scattering. In the structured beam, if you move laterally your beam, your sample inside your beam, you have a change of direction of the scattering. So what we did is suffice to take few positions, lateral positions within the beam. So basically we do 16 positions, and you can use the same algorithm that we did before for far field tachography, but instead of Fourier transform, we get a Fresnel transform. This is implemented in TypeI. It's also an open source. You can use this, and you can obtain the same information as we get before, phase, amplitude, probe. And if you combine this in 3D, you get the 3D map of the sample. And then just to show what you can do, I took a small sample of an alloy fabricated by additive manufacturing, basic 3D printing. What is nice here is that when you put a layer, cook with a laser, you cook again, another layer, cook again, but as you're cooking one layer, the layer below is getting annealed, and then you are changing the phases. So you can see here that from the bottom to the top is the direction of the building. You can go from as-casted to cellular, mixed, and eutectic metallic phases. This was done when 106 joules per millimeter square. If you change just slightly the power of the laser, you have a completely different phases. You have more dendrite. You see the dendrites there, the mixing of the different phases. Based on this, you can segment the different composition, different titanium phase, let's say, inside of this particle. And since we are quantitated as before, we can get the mass density of each element, which corresponds quite well to the values obtained by XRD or X-ray diffraction, this conditional X-ray diffraction. But this was done with a small sample, and we got the same results as the far field tachograph. What's the advantage of doing near field tachograph? That is the point. So think first that when you do nanoimaging, you take only pieces of a big sample. But if you take only pieces, you may misinterpret this meaning of those pieces when I put it together. Imagine those guys, people trying to touch the elephant. They don't know that it's an elephant. They can only access to one part. So their elephant at the end will look like more like this. So it's close to the reality, but it's not really the reality. So you need to be able to do nanoimaging without destroying the sample really. So that's the point of doing near field tachography, because now I took again the particle of catalyst that I showed before, which I did not tell you before, that we could only scan a small hemisphere, a small part of these particles, because the technique was too slow. But since near field tachography is much faster, you can scan the whole particle, and you see that you have much more information that you could not see before. now you are like struggling to get this new information because this is very new data that we got on this Soleil at the SRF. Sorry, so we are still analyzing this data. And it's the same case for the cement. The cement looks beautiful here, but when you increase the size of your capillary to 200 or 300, you have a completely different structure of the cement that you could not see before. And if you look closely, you have these hollow crystals. Like you see like crystals with unhydrated and then a gap, and then the other hydration part. You have fine structures like this, which first proves our point that when the particle gets fully hydrated, the products go outwards. And those grains have not been observed before 2000. It was Hadley who observed those grains by electron microscopy, where you see these shells, empty shell, and you see a shell here with the unhydrated part inside. And when they get fully hydrated, you get an empty shell. What you get, these Hadley grains. This is the fourth time that one could see this in X-rays. So now it opens a new window for the community of cement, which was already very well explained by my colleague Luca Valentini on Monday. So you can ask him more about cement, but this really opens new pathways. So I need to be brief, but so tachograph, what I showed here is that really quantitative, provide high resolution, high sensitivity, high contrast, have two variants. It does not rely on plane waves or crystallinity. Retrieve composition and microstructure morphology. The next challenge is really increasing the speed of data acquisition or even the data analysis by artificial intelligence, mathematical optimization. But we already saw that you can do coherent imaging in a bending magnetic beamline, because at ESRF we are doing this at the BM2 beamline, but also Diamond is doing tachograph at B16. And we could do also a very large sample of 2 millimeters at ID19 beamline with Polta-Ferro a few years ago on a piece of teeth. Need to be optimized, but it was 2 millimeters, and with a beam of 100 microns, proving that it can scan large samples. So, of course, this is not one-man work. There are many people working with me, but I will not tell the name of everybody because sure, you forget. But the pictures of them are here. And if you need more information, you have my email that we are free to send me an email. My website where I put materials of the didactic or my presentation, my data analysis tool repository where I can get my softwares. So thank you for your attention. Just before closing, I just want to do some advertisement about the International Conference on Tomography of Materials and Structure, which will be in 2024 in Stellenbosch. Stellenbosch, sorry for the pronunciation. You know better than me this beautiful place. Thank you for your attention.
Thank you. Thank you for a very nice talk. It's actually very interesting stuff. And any questions for the speaker? Is there any in the chat?
I have a question.
Yes, Kuda.
Yes, thank you very much, Julio, for the very interesting talk. I just wanted to find out, I think I've heard people say before that with tachography, doing the experiment, you know, once you've done the experiment, then actually retrieving the data is not very easy. Is there now sort of a set way? Are there like algorithms and software that is done that someone can just sort of plug in their data and use?
It's a very good question, because in principle, it's something that we are working a lot, because tachography starting synchronous in the tomography side, it was 2010, but it's from 2015 that really doing some work. But from 2015 up to now, we already speed up by a factor 100 in the data analysis. And they are TypeI now is a very well-established library, and Diamond is working in a graphical interface, but it works already like as a plugin structure from Python. Of course, it's still Python, so you need a Jupyter Notebook or command line, but it's still very fast. To have an idea, if we have like 220 by 20 microns projection, for example, you can get to the phases in less than 1 second. So if you have more computers, you can do for 1,000 projections, but it's really fast. In a few hours, you can have already your data. But just to mention that a few years ago, it was the same situation for phase contrast image when Paganini algorithm was like very hard to implement. So I remember 2011, it was taking a lot of time. Today, it's like a push button, but it's a much older technique. So I hope that tachograph will go in the same direction as long as the people are investing on this, because if there's no investment, there will not be improvement. But today I can tell you that it's already like user friendly.
Okay. Oh, thank you very much.
Any other questions for the speaker? Then why don't we give him a round of applause? The thing.
Thank
I'd
you.
like to give people a thumbs up. And then why don't we take a 5-minute break? I apologize for the tea being cut short. And let's try to get back on track at 15:45. So five minutes from now. Thank you.
Thank you.
Robert, are you here? Oh yeah, I see. I see Robert is here. I'm going to make him co-host. Okay, Robert, why don't you start sharing your screen and we can start with your presentation. Hello, Robert, are you here? You're muted.
Sorry, is it me now, Robert Knudsen?
Yeah, Robert Knudsen, yes, go ahead.
Okay, thank you. Thank you very much. Let me just share my screen.
I guess I'm not doing very well with introductions. Robert Knudsen, University of Cape Town.
It's okay. I hear you. Can you see my screen now?
I can see you, but I can't see your presentation. So we're looking at your camera.
Okay.
There you go. Closer. There, perfect.
Okay, great. Thank you very much, Chair. Right, so this talk, of course, is going to be very different to the previous two talks, which I thoroughly enjoyed. It's really a whistle-stop tour of our electron microscopy facility at the University of Cape Town. Now, I think the reason this is so important in this particular forum is that the more and more we train people through the electron microscopy route, the more chance is that they will then be able to advance onto experiments in a synchrotron light source. So in many respects, we see this type of activity as a feeder into bigger things associated with synchrotron. Of course, it is a means to an end as well, as you well know. Let's try and get it. So for those who are perhaps not familiar with the southern tip of Africa, we're right down here in Cape Town, and that's a beautiful view of Table Mountain, our world-class soccer stadium over here, which is our multi facility. And the University of Cape Town is just on the other side of this mountain, on Devil's Peak. And of course, looking at it from the other angle looks exactly like this. And our electron microscope unit is on this lovely campus on the slopes of Devil's Peak Mountain. So that's where we are. This is what we look like when we sort of underground. We're the lowest level, partly underground, of one of our new engineering buildings. This level was purpose designed and built as an electron microscope unit, and consequently many of these labs containing our different microscopes have been designed to be vibration free and of course electromagnetic interference free in order to get the best out of the microscopes. And associated with all of this, of course, is sample prep and then our offices for our personnel. In terms of microscopes, just very quickly, on the scanning electron microscopy side of things, we've got a FEI Nova NanoSem, important detectors on it, an EDS system and an electron backscatter diffraction system. And it also has a STEM bright field, dark field, hard detector. Can also operate in low vacuum mode. And then perhaps our latest scanning electron microscope is the TestScan Mira 3, which also has a electron backscatter diffraction system on it. But more important, more uniquely in our unit is a electron beam lithography capability. And it also has a WeTech Raman confocal microscope attached to the SEM, and that microscope can be shifted onto the one end of the electron microscope chamber so that you can basically do simultaneous scanning electron microscopy imaging and Raman microscopy on the same specimen in the same chamber. Essentially correlative microscopy, and I'll show you an example of that a little bit later. On the transmission electron microscopy side of things, we have three microscopes, a FEI T20 with a Lab 6 filament, F10 and ILS capabilities, and a Technar F20 with a FEG gun source. and also it has a direct electron detector as the capture mode of this microscope. Both these microscopes are configured very well for biological sciences, particularly the F20 for cryo-TEM. Obviously not by any stretch of the imagination a top-end cryo-TEM, but it's one of our, essentially our feeder microscope into greater things for sending samples elsewhere in the world. And I'll talk a little bit at the end about that's where we should be going to. And then on the right-hand side is a new addition. It's a recent donation, in fact, from Sasol, the Techni Osiris microscope, which is a microscope configured for the material sciences. In particular, it has a 4 windowless STD EDX detectors, and of course it has STEM, RDIF, and F10 and EOS. Now, I think from the nature of our microscopes that I've just shown you, you'll already grasp the multidisciplinary type mode of our operation, which is really the message I want to get across for our unit. In terms of operational structure, we are in a very privileged position in that the University of Cape Town actually fully supports 7 full-time staff members in the unit. And that's broken down into myself as a director. And then because we integrate life sciences and material sciences in our unit, we have a microscopist and a research officer dedicated to each of these disciplines. But of course, there's a severe amount of overlap in the activity, and we generally all work together, although, of course, there are the specialisms at the 2 ends of this spectrum. And then supporting all of that, we have an in-house mechatronics engineer who does most of the maintenance and upkeep of our electron microscopes, and incredibly experienced in that regard, and a technical officer who then supports that person. So we're quite self-sufficient from that regard, although we, of course, do lean on OEMs and agents where necessary. Our operational structure as such, we, of course, recognize that materials, and this is perhaps focusing on the material sciences, that the actual materials and samples are developed and generated outside of the unit. So we rely on the activity of different academic departments or units and centers within our institution. We're working in different areas of chemical engineering, materials engineering, solid state physics, etc. And they would then arrive at our unit with their materials. We might assist with final prep. And then, of course, it moves to scanning electron microscopy or TEM, or indeed both. Generally, if we operate in a mode where the electron microscope unit is fully engaged beyond sample preparation stage, then one of our microscopists will, of course, get involved with assisting the researcher to use the microscope, obtain the relevant information. And then depending where that goes to, the research officer will then get involved with data processing, reporting, and of course, that may lead to research collaboration, publication, which of course we all want to be involved in, and all of those interactions may generate new ideas, and of course this cycle of life continues. Of course, we encourage our researchers to get involved with microscopy themselves. So whilst this green outline here indicates the role that our staff in our unit would play, ideally we want researchers to play more of a role in this space, and consequently we train them to be microscopists. And on the extreme end of the spectrum, we would actually get somebody coming in and basically on their own they would move through this entire process. And that for us is first prize at the end of the day, because it means we can effectively use the microscopes 24/7 and essentially sweat the assets. On the life sciences end, of course, a similar mode of operation. We would rely on folk producing materials outside of our unit, and of course we would assist particularly with the life science material with prep, and it may initially go a route of negative staining, etc., to optimize the sample, and this might be quite iterative, going backwards and forwards to optimize sample preparation. And then in cases where we would follow the cryo-electron microscopy route, protein analysis and similar, then we would then move towards cryo-electron microscopy sample prep, very sophisticated data acquisition, data processing, which we do in-house in our unit, and we've got experts to assist in that regard, and then the similar process of reporting and research collaboration. So again, this is our capability. Ideally, what we want to move towards, and I'll show you that at the end of this presentation, that we want to emphasize training more and more microscopists so that they're able to basically do much of this on their own and therefore drive their own research, make more use of the resources available to them, and move beyond. I'd like to just give you a summary now of not a summary really, but just a snapshot of some of our activities that we get involved with in terms of the multidisciplinary nature of our work in our electron microscope unit. And perhaps starting off, and I was very, very taken in by the talk by Can Yildirim on the texture analysis of grains within the bulk, which is something we've been hoping for many decades. But he did, of course, compare that often with electron backscatter diffraction, and this is one such example where we do a lot of work with EBSD. In particular, this is a large area map, something of the order of 4 by 1 millimeters. It's a hot rolled stainless steel, and this is a deformed, elongated microstructure. That's one part, that's the other part of the large area map. And of course, what we're interested in is measuring the texture, the preferred orientation of the grains within the polycrystalline microstructure, and identifying the different texture components that would occur in this microstructure. This is just a slice of the orientation distribution function, and can also refer to pole figures for representing the texture distributions. Well, why is that so important, and why is it important to develop these large area maps? Well, this shows us a higher res image of that same microstructure. And in fact, what we've done here is we've dissected it to extract different grain sizes, and we can then isolate the different grain size populations into the different texture components, and therefore eventually be able to illustrate how these texture components add up towards giving the material the plastic deformation that it displays. The use of Raman microscopy on the scanning electron microscope. Of course, I gave a hint earlier that it is in fact a microscope which allows us to do correlative microscopy. And this little picture just demonstrates that in the same chamber, you can basically move your sample between the Raman objective and, of course, the pole piece for the scanning electron microscope. And that's very helpful with being able to image at fairly high resolution and then to be able to identify an area that you might want to analyze from a molecular point of view using Raman spectroscopy. So an example, this is a fibrous material in the polymer matrix, reasonably low mag view on the left-hand side. This is just a conventional secondary electron image. and on the right-hand side, a higher mag view of this mushy part in the material, and essentially interested in the analysis of these fibers, as well as this complex matrix which contains a mat as well as a series of bubbles or open pores. And being able then to move into the space of the Raman confocal laser beam, you can then beam onto the same area that you were viewing in the scanning electron microscope image, and of course you can obtain Raman spectra and be able to identify the different constituents within this case the fiber, which is this red part, and of course looking inside one of these bubbles, which is indicated as blue, and then the matte surface itself, which is this matrix part in green. And we found this correlative space for operating both Raman and SEM at the same time incredibly valuable. Just another pretty picture of a similar type of analysis. In fact, it's the same fiber, and here we are just looking at the fiber itself, and then there's a casing on the fiber which was of interest. And once again, this important correlation between the actual SE or secondary electron image and the Raman microscope. The other unique feature of this particular test scan mirror microscope, of course, is the fact that we can do electron beam lithography, and that particularly allows us to develop nano fabrication techniques for electronic devices, biomedical applications, and also in some cases for catalysis. Now, I think everybody's familiar with the term lithography, of course, and the only difference here is, of course, we're using an electron beam effectively to excite the electron reactive resist, which is deposited on the substrate of interest, and then, of course, you can develop it, and you end up, in this case, with nanoelectronics, effectively making a circuit. Here you can see that same microscope I showed you earlier. This is the SEM chamber. That's the electron beam column at the back. And this, of course, is the confocal laser microscope now, which has been moved onto the top of that same chamber. Effectively, moving the sample backwards and forwards inside that chamber to either put it under the electron beam or in order to be able to develop it's careful how I use that word, develop, in order to be able to construct, for example, a nanoelectronic device, one would use this draw beam package on the microscope system to effectively plot out the areas that you want the electron beam to move over. You can see there's a 50 micron scale, so obviously accuracy and resolution is critically important, and you can map that out using a set of coordinates. And once you've done that, you can then, of course, effectively expose that electron reactive resist to the electron beam. As an example, if this were a substrate and you would previously deposit a polymeric layer onto that surface, pop that into the electron microscope, set it up with your draw beam program, and then of course you would move the beam over that particular area, and you would excite the polymer the regions where the beam has moved over the resist, and then you would develop that and effectively remove the polymer from these red zones which you scanned over, and then deposit a metallic layer, usually gold, over that, and eventually dissolve off the unwanted bits of the polymer and end up circuit. So that is part of the service that we offer in our unit in terms of our electron beam lithography activity. And of course, in doing so, we can create a negative layer as such, or a positive layer depending on the type of electron sensitive resist that we use on the substrate. Let's move over to the scope of the activities for TEM. First of all, look at analytical and material side, and I think most folks are probably familiar with this. Once again, because we have got two research officers, one expert in material science, the other one expert in the life sciences, we're able to offer fairly dedicated assistance to our users in either of these activities. On the material science side, this is just a T20 conventional TEM using the energy filtered or F10 in the conventional parallel illumination beam mode, and just an example of a cobalt titanium mixture of nanoparticles. And of course, using the F10, we can bring out, in this case, highlighting the presence of cobalt in that structure. On the Cyrus microscope, which is that much more sophisticated for material science, I'm just showing an example of our EDS, use of our 4 windowless STD EDS detectors in STEM mode. Just simply an example of, once again, looking at nanomaterials or nanoparticles for our catalysis researchers. And in this case, we're taking a hard-F image and, of course, mapping out, in this case, iridium, which is in red, and oxygen in blue, and on the right-hand side, iridium again in red, and tin in green. It's, of course, iridium nanoparticles on a tin oxide support. So, once again, just an example of demonstrating the versatility of our activity. On the biological side, of course, in terms of, and I've just termed it conventional transmission electron microscopy for the biological sciences, we have the ability to assist with sample prep, going through the route of high pressure freezer, freeze substitution, and then, of course, making ultra thin sections and viewing them in conventional bright field mode, in this case, in the transmission electron microscope, and then just some examples of cells, bacteria, and microfibrils of human hair. Another example of what we might term the conventional biological microscopy, looking at negative stained sample prep, and of course also looking at cryo images in the most conventional sense, where we've frozen and then made sections of that. The cryo-TM side of things, which is our upper end of biological microscopy in our unit. I think most folk are familiar with the role that cryo-EM has played in the COVID-19 pandemic. And of course, very early on, here is an example of a publication, 4th of March 2020, and very shortly afterwards, on the 13th of March 2020, a further development. Now, I'm not a life scientist, so I can't speak to the detail in these images, but essentially they are protein reconstructions as a result of following that route of cryo-electron microscopy, gathering multiple images, very, very sophisticated data analysis, which we are well equipped to do within our unit, and then, of course, the development of these molecule structures. Now, the resolution of some of this is pretty near atomic resolution. We haven't been able to operate at quite the same level because of the restrictions in-house in our own equipment, But because we're able to use our microscopes as feeder microscopes, we can send samples elsewhere in the world and, of course, get image capture and data capture at much, much higher resolution. This is just an example of some of the recent activity that's actually come out of our electron microscope unit. And there's no doubt that our local scientists have become quite well recognized for their work in biochemistry, particularly developing structural information following the cryo-electron microscopy route. Just in terms of our sort of workflow with regard to this particular activity at the University of Cape Town, of course, much of the interest and activity is developed outside of our electron microscope unit. We rely on the health sciences and scientists, and indeed people elsewhere in South Africa, of eventually developing the research questions and the materials. And then when it comes to our unit, we would assist in optimization of those samples. We would do some initial screening. We would do as much as we can do on our Techni F20 microscope. And then where necessary, we would indeed ship those samples elsewhere in the world and collect high resolution data. Now, once again, at the end of this presentation, I'll emphasize why we should also be doing things a little bit differently or more than just shipping samples off elsewhere. But the reconstructions would be done back here at the University of Cape Town. From a picture point of view, this is what it would effectively look like. Protein optimization, moving through our microscopes. We would, of course, optimize the cryo-grid preparation, and then there would be a number of iterations necessary to refine and optimize the sample. And we would then perhaps rely on microscopes elsewhere in the world. This is a Titan Cryos, upper end of the cryo-EM microscopes for the best possible resolution data acquisition. And this on the right-hand side is a picture of scientists working within our unit doing the data processing. Key is training, and I emphasize the fact that we don't just want to do work for other people, we want them to do work for themselves. We effectively want to provide the resources, but ideally we want to train enough people as possible to become microscopists themselves. And just a glossy picture of the type of activity, workshops usually attached to our local microscopy conference. We'll have another one of these conferences now coming up in December in Johannesburg. And of course, we train final year students and students at the honors level, both in the life sciences and material sciences. We provide solid introductions to electron microscopy. And then our hope is that when they follow the postgraduate route, they will get sufficiently encouraged to explore microscopy further and assist in solving their research questions. A particular training initiative at the moment is one supported by the Chan Zuckerberg Initiative, where we are particularly training people for cryo-EM, particular folk from Southern Africa, but we also have a possibility to take folk from further afield. I've just highlighted in yellow here, we aim to run a series of hands-on workshops and online training opportunities and provide an information resource for scientists in the Southern African region. What we're doing in this regard, and we're currently in year one, is we actually bring scientists into our unit for a period of 2 weeks. And the aim is that they would arrive with their own samples, so they've got an interest in what they want to analyze, and we take them through the full cryo-EM workflow, which is incredibly intense, but the whole plan is to not just simply do analysis for other folk, but to train them to do their own microscopy and their own analysis. And in this way, we will grow the community and the interest, and of course that will just continue to hopefully mushroom out and develop beyond electron microscopy. This is a snapshot of the current call we have on our website for this initiative, and if anybody's interested, they can visit the electron microscope unit website and in fact have a look at what that training initiative entails and perhaps how to join it. So far this year, we've actually completed the training of 5 people. Not only have we trained those 5 folk, but it's contributed to at least 1 paper output. We've had 1 international data collection. In other words, we've moved beyond our unit to submit those samples elsewhere in the world. And it's also contributed to the completion of 2 PhD theses.
Robert, you have like 1 or 2 minutes.
Yes, I'm just about finished. Looking forward then, of course, partnerships are critically important for us. I think we all acknowledge that we cannot survive on our own, so local partnerships, international partnerships are critically important. In terms of who uses our unit, about 70 to 75% of the use is actually the University of Cape Town, but then we have a large portion of other universities, mostly in South Africa, but beyond our borders as well, stretching as far afield as Nigeria, where we in fact get quite a number of requests for use of our instruments. So the networking is critically important. And I think the other important thing here is that effectively this 21% of other universities means that our University of Cape Town is actually very instrumental in subsidizing the work at other universities in Southern Africa and a little bit further afield. We are developing networks with the University of Pretoria and the University of KwaZulu-Natal, particularly in cryo-electron microscopy. And of course, we also have a very strong tie-up with the Center for High Resolution Transmission Electron Microscopy at Nelson Mandela University, which is in the Eastern Cape. From a material science point of view, we interact with them significantly. International partners, very important partners, Diamond Light Source, for example, at Oxford, the European Synchrotron Radiation Facility, and also the Center for Electron Microscopy at the Ohio State University. Looking forward, this is the last slide, I think, new microscopes, or the last little section. As we know, microscopes come and microscopes go, and we need over time, of course, to replace them. And it's a continuous ongoing business, and of course, a very expensive business. To date, we have now applied to our South African research infrastructure roadmap activity for a Talos Arctica cryo-TEM to boost what we can currently do on our Techni M20. Looking forward, of course, we want to obtain a FEGSEM for biological and material sciences. At some point, we're going to need to replace our analytical TEM for material sciences, and of course, constant upgrades for EDS and EVSD systems. Last slide, or last 2 slides. The rest of the world is very well endowed with top-end cryo-electron microscopes, the likes of the Cryos, Techni Cryos, and of course the Joel Cryo ARM. Africa has none of this. And given the nature of the activity that we're certainly promoting at the University of Cape Town through our unit in cryo-electron microscopy, we really need to be looking forward to Africa obtaining a high-end cryo-TEM, Cryos or cryo-ARM or something similar. And of course, as I mentioned at the start, this feeds into synchrotron analysis as the science develops. And Chair, I think that is my last slide.
Okay, thank you. Is there any quick questions for the speaker? You can just put them in the chat. And before I turn over to the chair of the rest of the session, if I can be allowed to ask one quick question of the speaker. And that is when you spoke of the future scoping of your center, is there a way for your unit, the EMU, and the African Light Source to collaborate to put the planning for your future into our CDR and maybe the follow-on document, our technical, our TDR, and also how to establish an electron microscopy unit at any given university? I know there's some papers out there about that, but could we elaborate on that in our CDR? You think that's possible, doable?
So a quick answer, and I don't know enough about this perhaps, but a quick answer is I believe that our cryo-electron microscopists certainly are in touch with the African Light Source consortium. Particularly because we make use of synchrotrons elsewhere in the world through the South African government arrangements. I think there's quite a bit of conversation that happens there. So I agree with you. I think we should push the synergy a lot harder. And I think of course, the strength works both ways. In terms of supporting development of electron microscope units elsewhere, our Microscopy Society of Southern Africa, which is very active in the rest of Africa, Professor Rodney Genga from Wits University in Johannesburg, they developed the African Microscopy Network. And in fact, we've got a strong delegation attending our local conference in Johannesburg in December. And the whole plan there is to assist microscope units to develop through the rest of Africa and to develop microscopy societies to improve networking. So I think there is quite a lot on the go at the moment.
Okay, thank you. We'll be in touch on that. So why don't I turn over to the next session chair is Dr. Jian Kamal of Sesame.
Yes, hello, Lawrence, do you hear me? Hello?
Yes, I can hear you.
Perfect. So thank you. Actually, it's quite weird to be chairing this session while I'm also a speaker, but this is how cooperation can go on. So good day to all the organizers and the participants, as well as to all the supporters of having an African light source. I would say that this session is on Sesame, which is the only synchrotron facility in the Middle East and neighboring regions. It stands for Synchrotron Light for experimental science and applications in the Middle East, and having many similarities between the Middle East and neighboring regions with Africa concerning different skills and ambitions. Sesame and Africa started quite good cooperational phase that is growing positively day by day, and the official, or let's say the first official partnership started late 2021 by signing the first MOU between Sesame and the African Light Source Foundation. In this session, we are highlighting the scientific opportunities those Sesame can offer. And we start by the Sesame Scientific Director, Dr. Andrea Lausi. Andrea joined Sesame in March 2020, and he has been working at the Italian synchrotron facility, Elettra, where he has been in charge of several hard X-ray beamlines and projects, among them also the participation of Elettra to the LAMP project. I believe that you heard about this project the first days. From 2017 to 2020, he also coordinated all the communication activities in Elettra. Andrea, the floor is yours.
Thank you. I assume that you can hear me. And
yes.
So now I try to share my screen and find where is PowerPoint. Microsoft PowerPoint, certainly. Okay, do you see the slides in the proper way, I hope?
Yes.
So
yes.
I will try to give you an overview where we are, where we come from, where we are, and possibly where we are going at Sesame in a few slides. not too difficult because I am allowed to speak of each and every beamline that will be then investigated more closely by the beamline scientists, because Sesame is a relatively young facility. So we have at the moment 5 beamlines plus a 6th one, which is in the pipeline. So I will be allowed to speak of all of them with not detail, but at least to quote them where they are. So Sesame, for those who are not familiar with this facility, is located in Jordan, northwest of the capital Amman, and was developed like CERN under the auspices of UNESCO. And it actually takes, as you can see from the picture, takes its shape from the UNESCO logo. So you enter a place which has a strong imprinting of international cooperation for culture and science. And like CERN, Sesame is made up of members and observers. So the members are regional, so Pakistan, Iran, Turkey, Palestine, Cyprus, Jordan, Israel, and Egypt. Those are countries which sometimes, to find themselves on opposite sides of the political landscape. But it also has a large number of observers. So practically a large part of the population of the world is observer to Sesame. And the support and the contribution of the observer have been quite vital in setting up Sesame in the past years. So this slide summarizes a bit some of the main contributions which have been provided by the observers. So around the very famous story of the boat bringing Bessie 1, the old German synchrotron, from Berlin to Aqaba in order to be rebuilt in the Middle East. That was, let's say, the funding story of the construction of Sesame. And it was so successful as a story that there is a lot of people who still think that Sesame is Bessie 1 reconstructed in the Middle East, which I must say is not at all. We will return on this point later. But around the boat, you can see, let's go clockwise, the Sergio Fubini guest house, which has entered into operation, if you can call it operations, at the end of 2019. So it was finished just before COVID and before everybody was started to mail in for samples. But finally now it's starting to be used again by users which are coming to Sesame after the pandemic interruption. Then a little bit lower, the monochromator, which was donated by Diamond for the EXA beamline. The 4 RF cavities, which were a donation from Italy again, and these are, as you can see, for those who are familiar with these are Electra models, were built under the supervision of Electra in Italy and donated by the Ministry of Foreign Affairs and INFN. To Sesame. The entire material science beamline from Switzerland, that was the beamline that on PSI was making both tomography and powder diffraction, and we have rebuilt it here as a purely powder diffraction instrument, because as you will see, we have another beamline for tomography. And the Rosendorf's beamline, which was a CRG beamline of the Humboldt Rosendorf in ESRF, which was again dismantled and put together again as our EXA beamline in Sesame. And above all, the solar power plant, which was a donation, a very, very important donation from EU, which allowed us to be the only synchrotron in the world which is now provided by energy completely without with a very low carbon impact and also a very low impact of the problems for energy that are rising all over Europe and neighboring countries in this moment. So this we could not work without that. The bill for electricity went down from a few millions to practically less than $200,000 per year. So an incredibly important support for us. This this amount of donations from the observers is also reflected, as you can see here, in the attendance to the opening ceremony of Sesame in 2017, where around the King of Jordan, Abdullah II, you can see a delegation formed of international observers and stakeholders from directors generals of CERN. There is a sort of tradition that the president of the Council of Sesame is always a former director general of CERN. So the only Avic Shopper is missing in this picture, and but we have Chris Levin and the Rolf Boyer and Fabiola Gianotti, and the Director General of UNESCO, the European Commission of Science and Research, and delegates from the members, and Princess Subaya. So, and the directors of Sesame. So I think that this picture more than other shows how much the let's say the challenge of building Sesame and making Sesame work has been felt at an international level. About the Sesame energy balance, as I already remember, the footprint is tremendously low, and we pay tons, several thousand tons of CO2 every year, and also the amount of funding spared allows us to work. Without this, it wouldn't be possible. Now, we were saying that this is not SPECI-1 reconstructed. So this is true. The idea of having a low energy machine rebuilt in the Middle East, for how fascinating it was, would have left the region without Arctic trades, which are in any case quite a powerhouse for synchronization facilities. So after a debate, the members agreed to build a machine at 2.5 GP, third generation, so with space also for undulators and wigglers around it. And the design was taken over by Dieter Einfeld, so the father of the fourth generation of the multiband achromat, and who designed the ring. It is, I would say, with two band achromats, is the best machine that can be designed with a circumference of 133 meters. It's perfectly in line with all the other the best third generation machines in the world. The beamlines. So what you in 2017 was inaugurated in 2018, we started open the beamlines to the users. So going counterclockwise around the ring, we start with bending magnet number 2, so the infrared microspectroscopy beamline, which is Jian, which will present after me, where is the beamline scientist, and the beamline is using both the edge radiation and the bending magnet radiation. It spans an energy range between 2 and 25 microns in wavelength. And as you see here, it has a very typical design. So there is a sort of periscope path of the infrared from inside to outside radially with respect to the machine, thanks to a first mirror which intercepts the infrared radiation while letting the X-ray passing through. Once you are outside, there is a box coupling this beam to a microscope and a SDR spectrometer outside in the experimental arch. The first paper was published relatively quickly in February 2020. That was a study on preeclampsia. So preeclampsia is let's say, how to say it? It's a placenta disease of very difficult identification. So the study is it's trying to find out ways of informing ourselves on what kind of modifications in the proteins are accompanying this this disease in order to have a diagnostic tool for that. Okay, then going around the ring, you will encounter then the bending magnet number 8, the X-ray fluorescence beamline. So this is an X-ray beamline, and the X-ray fluorescence comes for free with it. It has been opened. This is the first beamline open to the users. This is the donation from President Rosendorf to the Robel beamline in the SRF CRG, and it spans an energy range from 4.7 to 30 keV, and it is obviously a trademark of synchrotron radiation. So to have an X-ray beamline is, let's say, one of the first things that you actually do when you build a synchrotron, because it's a technique which needs a synchrotron to be implemented, because you need to change the energy of the impinging beam. Also here, it was relatively rapid, the publication of the first paper, and this comes in the field of chemical studies on CO2 reforming, which are the most of our users for EXS beamline are in this kind of catalysis and chemical fields. Not only, but this is quite a trend for the moment. Then we can continue to the MS beamline, this is the material science. This material science. This is the first beamline with a from a bending from an insertion device, and so you see here both the wiggler, which is inside, and the experimental hatch with the theta to theta diffractometer with a donated Dectix Pilatus detector on it. The range is 5 to 25 dB, and it was open to users in December 2020. It's been quite an effort from the beamline scientists and the team of Sesame to put this into operation during the hardest period of the pandemic, but it was successful, and this success has been followed by a very rapid publication already in June 2021. I'm sorry, it's clearly a typo. It was not first published, then measured. And so this is a metal-organic framework study on capture of CO2 done by a group in Jordan, which was at the time the only group the only kind of user which could come to Sesame because the airport was still closed. Oh, this is a repetition. So all in all, with these 3 beamlines, we have received so far 461 total proposals, which are divided geographically, as you see in this pie chart. Of these 461, we have accepted, thanks to the effort of our proposal review panel, 256 proposals in total. I would say this is a quite healthy number. So it's around half of the proposals are accepted and half of the proposals are rejected, which is a good point, because a good middle point in which you are definitely selecting the best proposal, but also not rejecting too many proposals, which would discourage community which is being formed in these times. Yet it's obviously not a mature community of users. Many of our users are just coming for the first time to the synchrotron, so they are in the learning process of using the data to make paper. This reflects on the publications. So the number of publications is quite encouraging. So we have at this moment already 61 peer-reviewed papers, and it is still growing. I foresee a dip in 1 or 2 years when the effect of the less number of measurements during the pandemic will come out. But for now, we are still definitely growing. The average impact factor is 5.2, which is, in my opinion, quite good. And 30% of the publications have an impact factor higher than 7, which is particularly good as an average. So one can notice that also that 85% of the papers have one of the beamline scientists of Sesame as an author. This is a quite rare amongst radiation facilities, because it's a much higher percentage than in the mature facilities, but it's very well justified by the extra effort that the beamline scientists have to put in helping the users, not only in setting up their measurements and mounting the sample, judging if the data which are being taken are of good quality, but also in analyzing the data and sometimes even cooperating in writing the papers in detail. So this most probably will change with time, but at the moment this is the situation. If you think that we have at the moment 2 beamline scientists per beamline, you can imagine that our scientists are quite busy all year round. So ID10, the next step. There are 2 beamlines which are coming up next year. One of it is BEATS, the Beamline for Tomography at Sesame. This is a EU-funded grant for the construction, for the design and the construction of a tomography beamline, state-of-the-art. And the project is led by ESRF and has all these members that you see that you see here from ALVA to the Cyprus Institute. So well-established synchrotron radiation sources in Europe, plus some two institutions in the Middle East, and two, let's say, younger European facilities like Solaris and ALVA, which do not have or do not have at the moment in which this project was presented tomography beamline. So it was expected that the outcome of the BEADS project would be of benefit for all facilities, and in particular for Sesame, obviously, and Solaris and ALVA. So the status is very encouraging. In the previous here, you could see the triple Wiggler, which is the source. It's a wavelength shifter at 3 Tesla, which allows us to reach very high energies at the experimental station. Is already in place, as well as the front end. We are just closing the roof of the ring in these days after the shutdown, in which we have completed the installation of the front end, so that now we can concentrate on what remains outside. But all components have been procured. We are still waiting the crystals, so the multi-layers for the monochromator, but the monochromator is already here, and so is the stage for the detector, and we are still waiting at some part of the sample stage, but most of everything is already here, and we will finalize the construction during spring 2023, and we plan to open the beamline for users possibly in the second half of 2023. Nearby, one exit after ID11, ID11 left is the Helmholtz beamline. This is an initiative of the Association of Helmholtz Institute in Germany. This is a donation of an entire soft X-ray beamline, which has been built in Germany, and it has been transferred to Sesame as a new installation. The source is an Apple II undulator, which covers, let's say, from 70 to 2000 EV, and has obviously the possibility to change the polarization of the beam. And this has already been, and this is a refurbished, completely refurbished undulator from Betsy 2. The beamline has been already completely mounted, installed, pumped, and tested. We are waiting for the end of this shutdown to finalize the calibration of the monochromator and start welcoming the first friendly users within this year. So to open during the first call of 2023 for measurements in the second half of 2023, the beamline to the users. The experimental chamber is a simple experimental chamber with a photon detector. And you can also always measure the photocurrent of the sample, so the yield of fluorescence from the sample, and from and the yield of photoelectron emission from the sample. So it will essentially do for the moment next ups and next up studies. What about photo emission? Well, there is a plan for that because this beamline has a switching mirror after the monochromator, and taking advantage of that, a second branch is being designed in this moment in Turkey, and this is, let's say, a change of business model also for Sesame. So all beamlines so far are entirely managed by the facility itself. TechPet, the Turkish X-ray photo emission spectroscopy beamline, which is a second branch of the HESER beamline, will be dedicated to photo emission and will be the very first beamline built in the Middle East and managed in Sesame by one of the members. So it's a kind of CRG, let's say, beamline that could improve the number of beamlines in the future. So imagine if all members start building their own beamline guided by their own interests, that would populate the ring much more rapidly than if we have to take charge of all of them in the future. Okay, so training. We do a large amount of training. We did in the past a lot, especially we received a lot of training through several projects, especially from Europe, just to quote one, Open Sesame, which was led by ESRF and was a 2 million project for the training of our user community and of our technicians and scientists. And it is now finished. So it is now time to make of Sesame itself a training center and start receiving guests for learning how to use synchrotron radiation. So last year, so 1 year ago, we organized together with the African Light Source, ESRF, IAEA, the Cyprus Institute, and the LAMP project, a school at ITTP for synchrotron radiation, light sources, and applications. Well, I must say the lion's share was of Jihan Kamel and Metaud Hafush, who gave 7 + 7, 14 out of 40 hours of lectures. So it was sort of school of synchrotron radiation with a strong focus on data analysis on 2 of the beamlines of Sesame, writing with the idea, as I mentioned before, to transmit the knowledge of data analysis to the potential users of our facilities and of other facilities around the world. This school will be repeated next year. So the new edition, just 5 minutes ago, I remembered to change the QR code. So that this is correct. And this is the QR code will actually drive you to the new edition, which will be online. This is an online school. It's a beautiful meeting from the...
Andrea?
Yes?
Like 5 minutes more?
Yeah, perfect. Thank you. So from the end of January to the beginning of February, so from 23rd of 1st to the 3rd of February. We also did organize together with the Canadian Light Source and LAMP a sort of outreach program. So it's a workshop for high school teachers, which was extremely successful in January 2022, and we would like to repeat this experience in the future very much. As you had remembered, we also have signed the first MOU between a synchrotron radiation facility and the African Light Source, and we are trying to make plans as much as possible to improve the capabilities of teaching at our beamlines hands-on. Clearly, as I mentioned before, we have a limited amount of human resources. So what we are trying to do is to get the support from other European facilities in order to build schools which use Sesame as the stage for, or mainly Sesame as the stage for hands-on schools for synchrotron radiation. So I would just end here for once in time with the message of optimism for Sesame. So Sesame has become a reality. I acknowledge that it took a certain number of years to get here, but now it is a reality. It's operational, it's performing well, it's producing science, and we should do our best to develop it as a training center, not only for this region, but also for the African light source and beyond. Thank you.
Thank you so much, Andrea. I don't know if there are questions. Please, if there's any question, you can drop it in the chat window. Okay, I see 2 questions. Maybe we can take that. Thank you, Tsepo. So there is a comment from Tsepo that says, nice presentation, 2 questions. The first one, you have indicated that around 50% of the applications were rejected. Was this due to oversubscription or just the science case? And which of the beamlines is over subscribed?
Okay, this is due to oversubscription.
Yeah, this is the first. Yeah,
it's the first. So it's oversubscription, not it is. You never leave photons not to be used. So all beamlines are oversubscribed. This is a particularly critical moment with the call which has just ended, because we were late in completing the previous calls due to the difficulty in traveling and in sending samples. So, for example, XAPS was really oversubscribed, IR as well, and MS is not yet enough known, in my opinion. Normally, power diffraction beamline is the power horse of everything. Synchrotron, the fact that it is not yet so much oversubscribed as the other is just that it came online during the pandemic, so it still does not have the visibility that the other 2 beamlines have benefited of in the past.
Yeah.
For the second question, which I can read to everybody if you want, is the Middle East beginning to see the benefits of hosting such a facility in terms of retaining bright mind, number of graduates emanating from the use of the facility, etc.? No, this is very painful to say, but the pandemic has hit quite severely the educational system. For example, in Jordan, the number of students has decreased by a large factor. So it's difficult to find students in this moment, because there has been a sort of limbo for 2020 and 2021. So we have to judge the effect of Sesame over a period of 4 years. And 2 of these years have been quite destructive. So we still hope that, and I'm really convinced that a facility like Sesame is beneficial in this sense, but let's say the circumstances have worked against this effect.
Thank you, Andrea. I don't see other questions in the chat or hands, but I thank you, and you're still with us. So if anyone has a problem, can drop it in the chat, please. So now we move to my colleague.
There is another question from
Philip.
About Philip. Yes, of course. I mean, ICTP is ICTP. The school is not a Middle East school. It's a school open to the world, like everything in ICTP.
All right, thank you.
You're welcome. Thank you.
Thank you, Andrea. Now we move to Dr. Masoud Harfouch, my colleague. Masoud is the senior beamline scientist of the EXAFS X-ray fluorescence beamline at Sesame. In 2003, he obtained his PhD in geomaterials in France. Then he joined Paul Scherrer Institute, and in the same year as a postdoc fellow, then he became the beamline scientist of the SuperExas beamline and the Swiss light source. As beamline scientist at Sesame, Dr. Harfouch has to deal with many research domains, and his personal research interests focus on air pollution, soils, contamination, and nuclear waste storage. Masoud, 30 minutes, please. Thank you.
Thank you, Jan. I'll try to stick to the time. I'm also involved in the AFLS project and somehow into the CDR with my colleagues Hitachi Abe and Peter Ngene. So anyway, I'm really proud to, sorry? Yeah.
Oh, I'm just resetting the recording.
Yeah, thank you. So I'm really looking forward to see this project reality as Sesame is now. So I'm really the specialist in the X-ray absorption fine structure technique and also the XRF technique in synchrotron. And I will briefly and nicely present the XAFS technique, or give the concept basics of the XAFS and the XRF techniques, because I know not everybody is willing to work with this or a specialist. Then I will briefly show the beamline and give some case studies that can be done with the XAFS technique. So, I mean, generally what we start from is what is happening when we shine with X-rays onto any matter. So many things are happening, among them absorption. So the photons are absorbed, or they are scattered, they can be diffracted, or electrons are flying around. And also we have fluorescence. I will just mention these two techniques, the spectroscopy, XAFS, and the XRF, including imaging. These two techniques are done with two different ways, or similar and different ways. For the XAFS can be done with two techniques, in the transmission mode or in fluorescence mode, and the fluorescence mode, it's only in one way, which is a fluorescence mode. So the basic concept of this technique is really looking for the binding electrons in the atoms. So we are very specific to the atom or the element. So what's happening is that when we shine with the photon X-rays with a given energy, this electron from a core shell is absorbing this energy and being ejected. Another electron from a higher shell is going to fill this vacant place of the ejected electron, and it will emit a photoelectron, and that's what we call XRF. It's depending on where this electron coming to fill the vacant place is coming. The K shell, if the electron is ejected from the K shell and the replacing one is coming from the L shell, we got the K alpha or K beta. Then we have, if it's coming from the higher shell, from the L, we have the L emission lines, like what we see in this figure here. So using an energy selective detector, all the photons ejected from a given electron are stored in one given slot of energy, and they're accumulated. With the time, we know what is what, or which emission line is related to each atom. So there is a fingerprint or a footprint of every electron energy, or every energy of electrons. Sometimes we have some overlapping, but thanks to the monochromatization of, or we say the ability to move the energy of in synchrotron light source in the beamline, we can distinguish between these elements by changing the binding energy. So we can do more than that. We can map the sample and can see the distribution of each element in the sample, and also can look at their correlation. Like, for example, we see here in this example that is given just for education, we can see that titanium, for example, titanium and cesium are more colorated, or the calcium is not. So this is one way to see at least first how the structure is done. So this is a first step into going to the structure. But so this technique is applied in wide, very wide range. So it goes from sedimentary, petrology, soils, mining, ceramics, metallurgy for quality control, for example, petroleum industry, cultural heritage, archaeology, paleontology, whatever, because we are dealing here with atoms. So whenever you have a sample and you want to know the element that are in your sample, or more than that, you want to know the concentration of this element in your samples, you just go with the XRF. You know what is you choose the energy that you use, and then you can find out what are the elements that are in your sample and what is the concentration of each element there. So it can be really, we can detect and measure major elements in percents, or we can go down to lower than ppm. Sometimes we can go with a ppb. The other technique, it's called EXAFS. It stands for X-ray absorption fine structure. The concept is exactly the same. It's based on X-rays photon energy that hits a sample with a given energy. In this case, we scan the energy, and while this energy of the photons is higher than the binding energy of the electron, this electron is going to absorb this energy and to be ejected to the continuum and beyond. So what is happening is that we have some of this energy that is shining on the sample is going to be absorbed, and we have a jump like this in we call the absorption edge. So I'm trying to make it very easy so that you know the concept from it. So what's happening when this electron is ejected out? It releases it makes a photon, an electron wave or a photoelectron wave that is going to propagate in the vicinity of the atom, and then generally when we have an atom, it's never by itself. So what's going to happen is that this photoelectron wave is going to be backscattered by the neighboring atoms, and a signal like that is going to be generated. So then we have two waves. One electron wave that is going from the absorbing atom, or where the electron is ejected, to outside, and then there is another one that is backscattered by the neighboring. And we have then multitude of forms of this wave. There is one of them is what we call in phase, that the ongoing and the outcoming, the ongoing and the coming back are at same. They have the same phase, and then we have what we call a constructive wave. Then there is a slight shift between the two, and we have different signals until we have a complete destructive wave, where the two waves are opposite. So just by doing mathematical modeling, we using the Beer-Lemberg law for the absorption, we can convert the energy into a K wave vector, and we have what we call the EXAFS formula. You don't have to go deep. I just at the moment just look. We have two terms here. This term here and the other one. So it's a sum of all the electron waves that are from each atom, and we have the first part, which is what we call this is the phase shift, and the normal one, where we have the distance between the atoms, the number of the atoms, and the thermal agitation or thermal movement of the atoms. So with this one, if we do a mathematical modeling, we can get out or get all these parameters, like the number of atoms, the type of the atoms, and also the distances between the absorbing atom and the different atoms. So the XFs, or what we call XAFs, which stand for X-ray absorption fine structure spectrum, looks like this. And generally, it's divided into 2 parts. Some people, they divide it into 3 parts because there is a pre-etch here, but there are 2 main parts. And in these 2 main parts, we have what we call exinus. And the exinus is used mainly for getting the oxidation state, the symmetry, and also the coordination chemistry of the absorbing atom and the orbital occupancy. If we go to the backscatter atoms, or the wave getting from the backscattering atoms, we got what we call the XAFs, which stand for extend X-ray absorption fine structure. When we do the radial distribution or the Fourier transform of this signal, from there we can get the number of the atoms for each distances. For example, at this distance we have oxygens, we have nickel, and the oxygens and nickel, and this is a way to work in or to get the structure. Although if we are in a complete amorphous structure, so this technique is really the or the best technique to work or to find out the structure or at the angstrom level in non-crystalline structures. So where we use this technique, it's used, as I said, in a large domain in the environmental science, in the agriculture for contaminations or for plants, in the energy, classical or renewable, in the geology and geophysics, cultural heritage, medical and pharmaceutical studies, and so on. So almost all the fields wherever we have to deal with the fine structure or with the atoms. The advantage of this technique, I'm going to list them here together with the disadvantage in red. So as I mentioned, it's really highly sensitive to the local distortion. So it's very local, and it's elemental selective. We choose the element that we are more willing to work with. If it's iron, for example, and it's in an amorphous structure, we just will go to the iron edge. We probe the structure around the iron atom. It's also, it can give the oxidation state. It's very sensitive to the oxidation state, where it is where we have, for example, the chromium 6, chromium 3. One is toxic, the other one is not, and so on. It helps him to get in the oxidation state, also the symmetry. It can be used for solid, liquid, and gas materials. There also, it's not only that, it's you can probe just very local. So, and also you don't have to prepare your sample. You can use the sample as it is. The preparation is very minor, unless if you have concentrated samples and you want to do transmission, then you can make pellets or so on. Then we have a small, let's say the one of disadvantages is that we deal with a short and medium range order. We go just to a few angstroms, 3, 4, or 5 angstroms maximum, especially if we have a distorted structure. Then I think if we cannot go more than 3, 4 angstroms. The disadvantage, the major disadvantage, Andrea just mentioned it before, is that we have just few beamlines. It can be done only at synchrotron, and we have just few beamlines in each synchrotron, and also in the world. And these beamlines, the XAFs beamlines, are always oversubscribed. So and the all what we say, the advantage or the big advantage of this technique is not destructive technique. I cannot assume that it's non-invasive, but it's to some extent 90% of the time is a non-invasive technique. The XAFS beamline, which is PM08 XAFS XRF beamline, is a donation from Robel. All the components that you see here are donation from the Robel beamline that was installed at ESRF before, CRG beamline. Thanks to my colleague Andreas Scheinost, we could get these components as a donation. We installed them, and we have really good things out of it. We changed this monochromator here. This is an old one. We changed the new one from donation from Diamond. We adapted this beamline to all these optics to our parameters of the storage ring, and these are the parameters that we have. The last two parts are not; they're still designed, so we don't have the optics to go really down with the micro. Sorry, this was another one. So at this beamline, we can focus the beam down to 8 by 10 microns, but we don't have yet the optics for that. So it's in the design, but it's not yet done. The experimental station of this beamline is completely new, and we have ionization chambers that we fill with the noble gas for detection. For a transmission mode, you can see here the sample holder and the ionization chamber before and after the sample. Another ionization chamber for the reference, and we have a fluorescence detector. Actually, we have two fluorescence detectors. We have a single element K-Tech detector, which we bought ourselves, and we have what we call it an INFN detector. It's a collaboration between Sesame, Electra, and INFN from Italy for a 64 ray element detector. And up to now, it's working well. We have good results from there. And we have the monochromator that we have now. The new one has two pair of crystals, silicon 111 and silicon 311 for high energies and higher resolution. We can go from 4.7 to 30 kiloelectron volts with a beam that is now just slit down. We don't have focusing system, or it is designed to have it. And we can go from 2 by 2 square millimeter to a larger beam. And we can cover mostly all the periodic table with a K edge from titanium to indium. Tin antimony also can be done if we force a little bit, push the limits. Then we can do the L edges from cesium up to lanthanides and actinides. Just want to mention for the actinides, only natural actinides, which are uranium and thorium, are accepted with very low concentrations. So we are done with the technique and the beamline that can be used for this technique. And I go, if I have enough time, I can go with some of the examples. I will start with the first example that has not been done at our beamline, but then at another beamline where they could really focus the beam to a few micron square micrometer. Yeah. So this project has been done with Annick Freudwald from Polish Shear Institute, and has been done on the microXAFS beamline at the Swiss light source. So the fact is that we collected, or a sample was collected from a cladding that is used for feeding the nuclear power plants, and we call them, in here they put the fuel pellets in this cladding. They are put into the assembly storage, and they put it into a basin, into a swimming pool, to cool it down. So the sample was about 20 by 20 microns. And when we do the image or the CM, we see this part here, and you see that this is the sample that we have from the cladding. And when we look, there is on the top a cloud of something like corroded. So the tube is zirconium doped with the niobium. Then we wanted to see if there is any corrosion, if there is any oxidation or whatever is going, what is going on, that this changes the color. So we do a mapping in fluorescence mode, and we do a mapping of the sample at this region here. Then we went into a different position and we took the X-ups, Xynus plus X-ups. And at the lower part here, we could see that we have a metallic zirconium. And when we went a little bit up, we started seeing a change in the shape of the Xynus and also in the X-ups. And when we went on the top, we found that we are totally oxidized. So then there is when we do mapping, we can also do the mapping at different energies, since we have this tunability of the energy. So we can go to the pre-edge and the post-edge, and from there, if we do just subtract the two maps, we can really define the zone that is oxidized. So this is how we can apply this technique and combine the two techniques, XRF and XAFs. The second example, I want to add another technique to that my colleague Mahmoud is going to talk about later on. And this is a project that has been done also at the Paul Scherrer Institute together with my colleague Marika Vespa. She's now at KIT in Germany, Karlsruhe Institute of Technology. So this is for nuclear waste storage, and this is about cobalt that is used in hospitals. And since it's radioactive, we have to store it in cement. And it has been prepared with two different techniques. In the first technique, we put the cement with water, and then we add the cobalt. In the other technique, we put the cobalt, cement, and the water together and mix everything together. When we do a micro XRF, you have a kind of ring and the hot spots. And this is really dependent of the technique, how you put or you mix the elements. Or when you do a micro X-ray diffraction, when you can combine micro X-ray diffraction in the same beamline, if you have just a detector. But with the micro XRD, we could just find for both samples just cobalt hydroxide, and the other phases that could be amorphous to X-rays are not detectable. Then we went with Xynus and XAFs, or full XAFs, at 2 points. One with one technique, with one mixing technique, and the other mixing technique, and we observed already a shift into the edge for the Xynus in the white line. And when we analyzed the XAFs data, we found that there are different distances from the neighbors. I mean, the surrounding neighbors, they are, of course, cobalt oxides and cobalt from each spot. But the distances are different, and this is typically the difference into the oxidation state that makes these distances longer or shorter. And then we found out that there are the two the cobalt is in one case it's cobalt 2 plus, and the other case it's cobalt 3 plus. One of the publications that has been coming out, Sesame, or this beamline, is a study on the influence of boron when it is going to be substituted to Mn. So, I mean, nowadays we are all looking for batteries with a very high performance, and that that lasts for long. And we start with the phones, for example, and cell phones, especially these last generations. We had generally a battery that lasts for a half a day if you use it, and nowadays we can go with the longer one, and that's thanks to the efforts of the people working on batteries. And Murat Askandir from Turkey was looking at trying to make these batteries lighter by substituting the boron to the manganese, and also having better performances. So he did the Xanes and the XFs on these ones, and by changing the ratio of boron and manganese, or the number of boron atoms replacing manganese, he could find that this by adding this boron, or substituting boron to manganese, he could get different structures in the cathode, and it forms lithium manganese 2 oxide, and this is very good electrochemical. It has very good electrochemical properties, and the formation of lithium manganese oxide 3 and lithium boron oxide, and also lithium manganese 2O4 crystals, and it's which gives a good intercalation and electrochemical property of the battery. So this is another example that has been done also at Sesame. So just I'm trying to make a variety of applications, just to show the different applications that can be. So from nuclear power plants to storage, nuclear waste storage, to energy batteries, and now into material science in medical applications. Nouf Mahmoud, she's from Jordan at Pharmaceutical University. She was looking into the gold nanorods in the treatment of cancer, cancer disease. So she prepared a different solution of nano gold particles. And she tried to look what is the behavior of that, and then when these nanoparticles, gold nanorods, are in polyacrylic acids, we start to see a slight shift into the edge of the Xanes, which is typical of starting of the oxidation. It is very small because the zone, or the part that is oxidized is very, very thin, less than it's just a few less than 1/10 of microns, and the penetration of the X-rays is more than that, so that we the gold, the nanoparticles is more, let's say it's more than the oxidized part on the surface. So, yes.
We have you have 4 minutes, please.
Oh, thank you. You see, when we do the XFs also, we could figure out that we have the oxidation state starts from at this PPA sample. We could quantify also, and we can see what is the number of atoms that has been, or the number of atoms oxidized of gold that are oxidized, and what is the distance of them. A last example is from Africa, and that's from Justice Okunda from Kenya, and he is trying to find out the methodology also to get as a kind of fingerprint for cancer diagnostics. And by looking for trace elements like iron, copper, and zinc, and he measured XRF and XFs in different samples from soft tissue and the urine. And by combining the two, or by looking at the correlation between these elements and then their concentrations in the soft tissues and the urines, he could find out, or this could be really a technique to follow up or to find out the cancer disease before that is really spread into the body. So just some statistics for the last call of proposals from this year that is going to be used for the next semester 2023. This beamline received 52 proposals, and 11 of them were from Africa. And the total accepted from all the submitted ones are 20, and 6 of them are from Africa. And this is how you see that Africa representation in Sesame or at the, at the XRF beamline, it's about 20%. And for the accepted proposals, we have 30% from Africa. Let's say this is really a high performance of the quality of proposals that are written from Africans also. Up to now, we have publication. This is the number of publications that has been done in collaboration with Sesame through this through myself on the XRF beamline. With this, I have to thank all the people involved in the beamline and also all the users from whom I got this this information. So if you want more information about the XAFS technique, you can visit these links. There's this International XAFS Society, which is very nice link, or also you can look at these books. And I suggest the one from XAFS for Everyone from Scott Kelvin. That's good, very good one. Thank you very much. And looking forward for questions.
Thank you so much, Masoud, for the presentation and for keeping the time as well. So there is actually 2 questions in the chat. So maybe you can have a look at them there, saving time.
Okay, where are they? I don't have them.
Simple. Okay, it's a very nice presentation.
What is the minimum?
You got it?
Yeah, what is the minimum quantity of sample that can be analyzed? Can it distinguish between different isotopes? Yes, for the first question, yes. The quantity is, I mean, it's very small. Generally, if you have higher concentration, it depends on the concentration that you have. If you have a higher concentration and you want to do transmission that is in the order of 10 milligrams up to 50 milligrams, depending on the concentration. If you don't have, if the concentration is very small, so that you try to make your sample thick, but the penetration is, as I said, is very, very minimal. It's about from 10 to 20 microns. Can it distinguish between different isotopes? No. We are just looking for the oxidation state, not the isotopes. It can give you the oxidation state, the redox state, the symmetry, but not the isotopes. Is there anyone?
Yes.
Is the XAFS technique always in conjunction with XRF analysis? Does it mean one needs to specify both techniques? No, they are completely independent. XRF, I use it generally as a, I will say it's a pre-characterization or pre-characterization technique to know what are the elements that you have, if you or what is the concentration of that. And it's not necessary to do that with XRF. You can do it also with ICP or AS or neutron activation. There are many techniques to do that. XAFS can be done if you pre-characterize your samples and you come and you say, yes, I have this element and I want to do XAFS. I want to look at the structure or the fine structure around the one element, or if you prepare a synthesis, if you synthesize something, as I showed in the previous one from boron replacing the manganese in the batteries, then you don't need the XRF at all. So this can be combined, but each technique can be done by itself. Yeah, so you can use whatever technique you want. Does XAFS technique need to have permanent magnet at the sample to solve spin states? No, not really. Unless if you are looking to if you want to follow the spin order in your magnetic samples or so.
Thank you, Masoud. The last request is to drop your email on the chat.
I will do it right now.
Thank you so much. So there's quite
sharing. Good.
Yeah, there is quite a delay in the program, but we can offer quick refreshments for 5 minutes, and please come back in 5 minutes. Thank you. Hello. I think we can resume our program of this session. And as I said in the beginning, I'm chairing, but I'm also a speaker of this session, being the Sesame Infrared beamline principal scientist. I had my PhD in Italy, 2011, and then I worked at the INFN at Daphne facility for the IR beamline. Then I joined Sesame 2015 to construct and operate the IR beamline. And recently, I'm also involved in the preparatory phases of the establishment of the first African light source. So what I'm going to speak about today is the infrared beamline of Sesame. I just need someone to confirm seeing my screen, please.
Yep.
Yes, perfect. Thank you. So Sesame infrared beamline, which is termed BM02, as was indicated in the presentation of the scientific director, Andrea Lausi, offers oasis of multidisciplinary domains, as I call that. The Fourier transform infrared spectroscopy technique, it's quite conventional and quite common and known in analytical chemistry. And it's basically a vibrational spectroscopic technique. Our target in this method is at the level of the molecules. And the method is basically relying on the absorption of the infrared radiation. And just to conclude this first slide, how an ideal technique can be used for a proper analysis, these are quite common tags for an ideal analytical method, which should be non-destructive, non-invasive, because sometimes we have rare or one-of-a-kind items, such as for cultural heritage or archaeological materials. Those you cannot easily prepare in the lab, and such as biological samples, for example. It should be fast, reliable, and cheap. It should be universal. That means different objects can be studied with minimal or no sample pre-treatment or preparation at all. It should be a versatile technique that gives local information of small areas. And it should be also able to detect very minute or trace quantities. That means it has to have high sensitivity level. And it should be also, or preferably to be, multi-elemental technique that simultaneously detect multiple components in one shot of measurements, such as for biological samples as well. And this is where we can routinely say that infrared spectroscopy technique can verify or validate all these requirements. So just to have it like a pocket, we have the Fourier transform infrared, which is a vibrational spectroscopy technique. You have also the requirement to have the infrared absorption. That should be a change in the molecular electric dipole moment. And the only IR active molecular bonds should vibrate. And this is the response that gives us the output of any spectrum. And with this spectra, we can, based on specific energies or wave numbers, we can identify a wide range of substances, whether organic or inorganic. What we do here is called the infrared microspectroscopy, which is microscopy coupled to the common spectroscopy technique. So this is why we combine it as microspectroscopy. We can use both conventional infrared sources, and we can also, for very specific experiments, we have to use the synchrotron IR radiation. So just to give you also the output of such a technique that is used for structural analysis, for quantitative analysis, qualitative electron energy levels, and for where non-destructive methods should be present. We can also get information on reaction kinetics, effect of temperature, pressure, or irradiation, and material aging, and this is very helpful in the domain of cultural heritage and archaeology. So basically, we use this technique to identify structure of materials, and from this structure, we can also identify interactions, properties, and functions. We can use the Glober, which is the conventional IR source, or the synchrotron radiation one. Here, what you see is that on the left side, as I said, we are doing microspectroscopy. It means we need a microscope, infrared microscope. So the one that you see here is visible and IR microscope as well. What we can do is differential interference contrast technique. We can do fluorescence, combined fluorescence with infrared. We can do chemical mapping with the IR radiation. We can do image analysis as well. So it's not anymore the typical spectra, the typical infrared spectra that we used to see. And the advantage also of this technique, since we have a microscope, that we can collect hundreds or thousands of spectra. So we don't anymore collect the 3 triplicate spectra of any sample that also goes on for the same point. Rather than that, we have a stage for the microscope that we can use to monitor or map a wide area of the sample. And this gives us much better statistics, especially when we work for applications like medicine. That's very important to have a reliable set of information on biological samples. For example, I gave you here this image that shows you the advantage of having chemical infrared maps. So on the left side, you see the histological images of biological tissues, but those to the right are the extracted or tailored infrared chemical maps for the biological tissues, identifying different regions also on the spectra. So we can get information on the proteins, on the lipids, on the nucleic acids such as DNA or RNA. And this is again very useful information. Just consider that it's something like geography. So this is also important to give us information on the concentration of these biomolecules. It gives us information on the distribution of these molecules as well, and the best statistics. This also is an example on chemical mapping of modern hair. You see to the right 2 cross sections of modern hair. And the one to the left is the infrared maps. Again, it gives information on the distribution of these analyzed biomolecules, such as proteins and lipids. This is another example of how this technique can help us identify or investigate some archaeological samples, such as the one I showed here is ancient human teeth, 5,000 years old. And what you can see here again, the colors of this map is showing us the concentration and the distribution. So for the synchrotron IR beamlines, we utilize the infrared region on the electromagnetic spectrum. And our aim is to extract mid-infrared, which goes from 2.5 to 25 microns, to the far infrared region and terahertz. And again, it depends on the extraction geometry of each beamline in each synchrotron facility. So for our beamline, for example, the IR beamline here, or in another also synchrotron facilities, we rely on the spatial resolution that we can get from the infrared microscope. We rely on the unique properties of the synchrotron radiation that is impossible to attain using the conventional IR sources, which allows to perform or conduct specially resolved or time-resolved studies. This is a comparison, a quick comparison between the conventional IR source and the synchrotron one. The global source, which is the conventional IR that you can find in any spectrometer, its range is from the mid to the far infrared, but it gives us quite it works at constant temperature because it's a hot filament like tungsten. And its flux is radiated in all directions. That means we don't have quite collimation or focusing. And to the right, you get the image of the synchrotron beamlines, which is basically produced by the relativistically accelerated charged particles, in our cases, electrons. The flux is radiated in tangential mode, which gives us a very collimated beam, which is very important for many specific applications and studies. And the flux here is directly proportional to the beam current. In our case now, it's 300 milliamp. So what you see here is the progress of the need for such beam lines by years. And just starting from 2017, we have, until now, we have more than 30 infrared beam line in different facilities. And the main advantage of the synchrotron IR radiation is defined by the high brightness of the synchrotron light, which is, just to say it in short, it's in the order of 100 to 1,000 times brighter than the conventional IR source. And this allowed important developments in both the mid and the far IR regions. So the beamline at Sesame was designed to be a day one beamline. We accept regular proposals. Those are submitted in our calls for proposals. We do in-house research collaborations with other researchers from all over the world. We offer sometimes training fellowships when there is quite available fund for that, and we get integrated also with international projects. This is a brief about the beamline, starting from the design validation step that was in 2016. Components were fabricated in France in 2017, and we started the installation and the beamline commissioning in 2018. The first results were obtained in April 2018, and the beamline came into service, was open to the users in November 2018. This is a top view of the beamline. And this is the inside the storage ring tunnel, the components of the beamline inside the tunnel, showing the extraction mirror and the focusing and deviating mirrors to the experimental hutch. So again, the most important aspect for us is the high brightness of the synchrotron IR. The super collimation, that means high spectral resolution. We can investigate smaller samples than ever, and we have better signal to noise ratios and faster data collection. And I just give you here two examples to imagine this. Imagine this, we are working on single biological cell that is very tiny entity. And if we go and tailor the conventional source to 6 by 6 microns, like the beam size, this is let me get the pointer. So this one is the global source. We collect 1,000 scans in 500 seconds, and this is the bad information that we get compared to the one to the right with the synchrotron at the same beam size, the same aperture 6 by 6 microns, with just 32 scans in 16 seconds, we get this very nice spectrum. Another example in solid state physics and mineralogy, this is a mineral sample, it's ocean basalt in diamond anvil cell at high pressure. and you just have a look at these two stat spectra. You see here with the lab Fourier transform infrared spectrometry with 60,000 scans in 16 hours. This is the total noise that we get represented in this spectra, and the one that's very smooth, very informative to us, we just collected in 2 minutes with the synchrotron IR with just 256 scans. So this shows you quickly how far the synchrotron IR is advanced with respect to the conventional and common IR spectroscopy one. Here, these are the performance of our beamline, and what you see here again, the superior advantage of the synchrotron IR, which is marked here in red with respect to the blue one, that is the global or the conventional IR, especially at lower aperture size. That means smaller beam size, and that means more specific applications to be done for when the collimation and focused beam is needed. And here again, you see the signal to noise ratio and the noise level that is in red, that shows the synchrotron noise, but this one in blue, which is far noisier than the red one, is that we get of the global source. This is the end station of the beamline where we usually do the experiments. And what we have now is a new end station that we received in a framework of MOU with the CHNet, Cultural Heritage Network in Italy. So the lab is now considered as a node belonging to the CHNet. And now we have this new microscope and spectrometer. It's Bruker end station Hyperion 3000 and Vertex 70V FTIR spectrometer. We have also the old end station that is also still operational at Sesame, but we are working in what we call it offline mode, which is the mode that we utilize only the conventional or the global IR source, which is still very useful to many applications as well. If you want to know more information about the technical aspects of the beamline, you're invited to check this paper, which gives information on our first infrared beamline at the Middle East. And as I always say, no matter what your sample is, the infrared macrospectroscopy technique is quite universal technique, since we basically target chemistry. And we have received a lot of demands from our users and collaborators working in different fields, those you see here, material science, cell biology, knowledge-based multifunctional materials, anthropology, forensic science, engineering, and so on. But the most two demanded domains, those we monitored here, are the life science and biotech, means biomedicine, pharmaceuticals, drug design. And also the second is the archaeology, bioarchaeology, and cultural heritage. Based on the samples format, we are able to cope in basic two sampling modes. Those are the reflection and the transmission. And here again, you can see that it depends on the sample form, whether it's liquid or solid or powder or film. We are able to cope with that because there are different accessories and different sub-sampling modes. Those we can tailor to suit the set of samples those the users come with, because samples have different, apart from having different formats, they also have different thickness, they have different status, they have different importance as well. When we, for example, speak about one of its kind archaeological sample. And what you see here is a different manipulation set. And these are the accessories, those I was speaking about. So we can measure in solid, in liquid, in film, We can also measure in gas status, but we don't have the gas cell so far at Sesame. We're trying to get to that as soon as possible. And we have also a set of commercial software that we can use to analyze the data. And for experienced users, I can allow also remote access from the users from anywhere to connect and process and analyze their data. And again, this is a pocket for a workflow for the technique, which basically starts with the samples preparation phase, then the data collection, which is very important, that has to be optimized as much as possible. And it's not the quantity of the spectra, it's the quality of the spectra that we are caring about. Then we go to the next phase, which is the data analysis, whether it's imaging or diagnosis phase. Our users are from Sesame members and also from Europe and other countries. And we saw also a good progress, a good growth of the beamline success measured by the users submitting their proposals to the Sesame call for proposals. From call 0 to call 4. In addition to the regular proposals, we also allow collaborations, and I'm also doing with my colleagues in-house research. I take you now to the last part of the presentation, which I focus here on the possible applications those we can work on, and some examples of our recent case studies. So it's what we have here is kind of a geographical disease map, and what happens what we can see here, okay, it's something that's related to the Middle East, but also Africa and other parts of the world. And recently we all had COVID, so geography is not anymore an important factor, I would say. So there are leading diseases. Those, for example, are like cardiovascular, cancer, chronic respiratory diseases, and diabetes. And we have a lot of targets. Those we can monitor and work on. So we have worked on diabetes here at Sesame. We worked on cancer. We worked on Alzheimer, for example, and we also worked on preeclampsia disease, which is a maternal disease. And this is again, Africa is part of us. And again, what you see here is human health problems also in Africa that needs a lot of attention and a lot of work to handle. Take you quickly to some of our case studies at Sesame. That was the first one that we published. We worked on the molecular structure of placenta and plasma in preeclampsia disease by this technique, microspectroscopy. And preeclampsia is a very critical disease that is difficult to understand its source or its cure, and whether the pregnant woman or the baby or both can die because of this disease. So we were trying to understand the role of the placenta in progressing this disease. Another study that we did also is that we worked on type 2 diabetes and diabetic nephropathy using the synchrotron IR microspectroscopy. We have also worked on Alzheimer in rat brain cortical tissues, investigating the effect of a particular seed, plant seed on slowing down the proteins responsible for the Alzheimer disease. Those are best known as amyloid and tau proteins. We also monitored the transcriptional modulations induced by proton irradiation that's related to a hormone. It's called the stress hormone. It's called leptin hormone. And this also has a good applications, for example, for astronomy or space physics. And that was also a good, that was actually the first beam time ever, the beamline with Italian group. Another pharmaceutical application, we characterized the mucoadhesive buccal films like of insulin. There was a nice spectroscopic analysis for that, and we are trying to progress this into industry. Maybe we can have it also produced as a product as well. These buccal films for diabetes disease. Another application in degenerative medicine, we worked on collagen nanofibers with a Turkish group. And again, two recent publications, again, one of them we worked on the preeclampsia with the same group, but this time we focused on the plasma. And the other recent study, we worked on breast cancer cells, trying to understand more the tumor-associated macrophages. This is the last publication that was, I think, last week we had it, that was on diabetic foot disease. And moving to cultural heritage and bioarchaeology, we had also this nice contribution from Cyprus and Turkey, exploring ancient human hair of 2,000 years old in Anatolia in Turkey, and we were monitoring the preservation status and alterations of organic compounds. Another interesting study on cultural heritage, we characterized textiles from a historical salt mine, an area called Shahribad and Zanjan in Iran. And this is a kind of a modern mummy. So I think in 2010, if I remember well, they were found some workers where the mine collapsed over them, and their bodies were preserved due to the salt. And we were working here on the clothes, those they were putting on at that time. They were very well preserved. Another study, we worked on historical Islamic parchment manuscripts. That was a collaboration between Iran and France. That was also interesting to characterize the paper, the manuscript degradation, because this is a historical one. And the ink that was used to write these manuscripts and some golden traces as framing these manuscripts. There was another study from Egypt on identification of pigments and binders in pharaonic coffin. We are still in the data analysis working on that. And with the same group, we worked also on mummification materials for a mummy from the New Kingdom from Egypt, still also on the data analysis. And this is a project that will be scheduled soon on removal the polymeric consolidant from inner wall. There is collaboration between Egypt and Belgium. And this is on organic dye components in Byzantine cloth fragments with users from Cyprus. And again, we have also a share in art restoration characterizing some Christian historical icons. And this is Ottoman wooden medallion that we are still analyzing its data. This from Petra, one of the very interesting and long-term studies. We are characterizing Nabatean wall paintings from the very well-known historical site in Jordan, Petra, as a collaboration between Jordan and Germany. And this is another bioarchaeological applications on hair, teeth, bones, and skin with users from Cyprus, Japan, and Turkey. And this is to take away information, again, to remember that it's a non-destructive technique. We combine both the spatial resolution of the IR visible microscope with the chemical sensitivity of the spectrometer. With the synchrotron infrared radiation, we can perform studies that cannot be achieved by conventional source. We can work on the microscopic scale, targeting the mid-infrared region. We can also target a lot of industrial applications. And with the small samples, those are found basically for cultural and bioarchaeological and archaeological applications. We can cope with that with the microscopic power. Many people are acknowledged for that, whether in Soleil, INFN, IAA, and Sesame. And I thank you so much for your attention. I put the stopwatch and I think I kept the time. I will be happy to take a question in the chat if there is any, and I will drop my email in the chat window in case later on you are interested to drop me a question. Thank you so much. And also, as per the our program, we move now to my colleague, Dr. Mahmoud Abdellatif, who's the principal beamline. Dr. Mahmoud Abdellatif is the principal beamline scientist for the material science beamline at Sesame. He received his PhD in 2013, material science and engineering from Trento University in Italy. Then he worked at the MCX beamline for X-ray diffraction in Electra. Then he also moved to Sesame in 2015 to be responsible for the constructing, commissioning, and operation of the MS beamline. Mahmoud.
Thank you very much, Jan.
And yeah, you have 30 minutes. Thank you.
Thank you very much. Just confirms that you hear me.
Yes, we hear you and we see your slides.
Okay, thank you. So it's the time back to return again to hard X-ray region. So after the infrared, after the presentation of Jihan. And it's my pleasure, actually, since I'm originally from Africa, when I hear that the word African light source, I always feel excited. So it's my pleasure actually to give this presentation. So so before starting, just a summary of the presentation, it will be about the just general description of the material science beamline at Sesame, which is basically the third beamline in row, historically in row after the EXAFs and after the infrared. And then I will give some selected example for experiments already done at the beamline. So let me start about the importance of X-ray. Everyone knows that every hard X-ray is important, but after this quite late time and late presentation, it's always better to start with history rather than science. So historically, since the discovery of hard X-rays, or since the discovery of X-rays in general, about 29 Nobel Prizes were given to the field of X-rays. So it means it's really important, the uses and the applications and how we can use X-rays to improve our life. So here is a list of Nobel Prizes in years, and you can just review this. I just picked this from the internet. So why we need hard X-rays, or why we need the material science beamline for hard X-ray diffraction? So in general, we need to understand why materials behave differently, and all materials basically are formed from atoms. So if we understand how atoms are arranged in this unit cell or crystal structure or in the space, we can return back to tune the properties of materials and to make a new materials, for example. So this is just an example that for any kind of application based on mechanical application like aircraft. And if you zoom by optical microscope, you will find out that there are some grains in the structure. So every grain is composed of a specific order, or better to say, orientation for atoms. And there is a unit cell which is repeated in this space in order to form the biggest structure. So X-ray or hard X-ray powder diffraction, actually we use it for understanding the unit cell, and then we can link this with the properties for materials. So when X-ray interact with matter, there are several phenomena occur, and we rely on the scattering phenomena. And scattering here comes from the electrons surrounding the atoms in the structure, in the atomic structure. And we can use this phenomena for reconstruction, for reconstructing atomic structure of materials. For example, if we have hard X-ray and we hit it by single crystal, for example, one specific orientation for all atoms, we will get something like points, and every point is constructive interference occurred between the scattered X-rays from the structure. And in general, the MS uses the polycrystalline material, or what we call powder diffraction technique. And powder diffraction technique is a set of single crystal, and we have all possible orientations. So instead of having one point here, we have, for every point, we have a ring, and every ring is a constructive interference conditions occurred in the experiment. So basically, what we obtain from the experiment, we just hit the sample by hard X-ray, and we collect the intensity for these interferences and the position for these interferences. And from this information, we have position for some peaks and we have intensities, and we can obtain some information related, for example, from the position we obtain the geometry of the crystal itself. For example, we have cubic, tetragonal, whatever the geometry in the unit cell, we can obtain it from the position. And the intensity of the peaks, they are more sensitive for the electronic distribution around the atoms. So this is the main information that we can obtain from the intensities. Also, the shape of the peaks is one of the critical parameters, because the shape itself, based on the microstructure details. So we know the structure, but we don't know exactly what is the microstructure, how the crystal size is small, and how the defects inside the crystals affecting the properties of these materials. So back to the MS, the technicality for the MS beamline, and so the MS beamline, as an idea, it came from the upgrade of the SLS material science beamline, and this beamline went to upgrade, I think, in 2010, and they started. Actually, I was not in Sesame at the time, and they started to think about the donating Sesame this beamline. So I started in Sesame in 2015, and I started with making the optimal use for the donated components, because not always having all components of the donated beamline that we can immediately use. It's better to study theoretically first what is the best, because we have different machines from SLS. And we had this study, and we changed what we couldn't use in terms of components, and we started with with what we can use, and then we have a layout, an optimal layout. So this beamline is based on a regular source, and it actually is the first insertion device source installed in Sesame. And this insertion device gives the advantage of having a very high flux compared to the bending magnet. Then we have a couple of mirrors. So the first collimating mirror is mainly to collimate the radiation after we have a divergent radiation from the source. Then we have a double crystal monochromator to select the energy of the beam based on the requirements of the experiment. Based on the from experiment to experiment, we can change the energy. Then we have another focusing mirror that we can tune and change the curvature for this mirror in order to focus the beam horizontally in the end, vertically in the end station. And the end station is based on a donated detector component from Dictor's company. It is an area detector. It's 300 Pilatus detector. And also the diffractometer was an old diffractometer in diamond synchrotrons. They didn't use it, and we had a lack of budget for completing the beamline. So we thought to refurbish this diffractometer to be in use for powder diffraction application. So this is just a schematic diagram for the optics hutch and for the experimental station. So the optics hutch is dedicated only for optical components at the beamline, whereas the end station is dedicated for that user can use and to put the sample and to obtain the experiment. So here is one picture for the wiggler after installation. It was in 2019, and this our engineers, they were testing, and as it was the first insertion device, we had to learn sometimes and to gain our experience using this and this is the optics hutch after completing the installation. So we have here, as I mentioned, the first mirror. So the beam is coming from this direction, from right to left, and we have a monochromator, and the monochromator mainly is to change the energy. And then we have a second mirror similar to the first one, with changing the face. So the first one is facing up, whereas the second one is facing down, and we can use the second crystal to focus the beam in the vertical direction. So historically, this is the first picture that we obtained after the monochromator for the monochromatic beam, and it was only inside the optics hutch. And this is the first experiment we did inside the end station as an XRF experiment, as a proof that it's a monochromatic beam. And at that time, we didn't have really end station completed, but we just put a very big sample, a very big sheet of metal, and we just ejected the beam. We tuned the energy before and after some edges, absorption edges, and in order to see the excited energy in this case. So it was the first proof that we have the monochromatic beam inside the end station. Here is how the end station looks like. So it was completed in December 2020, and so the diffractometer was, you could say, in-house diffractometer. So it was completely refurbished diffractometer. We have a detector here, so we have a place where we can put the sample in a capillaries, and the X-ray just hit the sample, and we collect the transmitted X-rays in this case. So the detector has an advantage also, that it's an area detector, so you can collect your experiment in a couple of seconds, and sometimes in a couple of minutes, based on the scattering quality of the sample itself. So here is a picture for the simulation, theoretical simulation before building the beam line, for the shape of the beam and the size of the beam at the end station or at the sample location. And here is experimentally, when we have the direct beam on the diffractometer on the detector, of course we had some filters in order to not burn the detector. And this is the profile, the vertical profile of the beam, and this is the horizontal profile. So as a full width at maximum, we have about 0.5 millimeter vertical size, 500 micrometer, and we have about 2000 micrometer in the horizontal size. This is the optimum size and condition of the beam that we can tune using the optics of the beam line. Here is a flux distribution as a function of the energy. So as a function, the beam line itself can be operated, say, practically from 7 to 25 kilo electron volts. With this acceptance, 23 milliradian, 0.23 milliradian, and 1.5 milliradian. So we can reach fluxes up to 10 to the power 13 photon per second for 10 and 15 kilo electron volt. As a matter of fact, that the distribution, the spectrum of from the source itself goes down with the energy. So also we have a less energy as a function of energy. So if we go higher energy, we decrease and we have less flux. But in any case, it's still high compared to very high flux compared to the conventional source. We could also tune the sagittal bender, which is sagittal crystal, second crystal of the monochromator, or in order to change and tune the horizontal size of the beam at the sample location, and also it has an effect on the energy resolution. So here there are two experiments. One was a flat sample, flat sagittal crystal, and the other one is for focused beam. So there, it has an impact, and we can. I already made the X-halves for one of the standard cover sources. Cover foils from the X-halves beamline, and you could see this the first pre-edge peak at the X-halves spectrum as a good indication that we have a good energy resolution at the beamline. This is a symbol diffraction experiment for a standard material. So the standard material is important in order to identify the contribution of the instrument inside before making a real experiment. So this is very important. And also the full width at a maximum for the peaks from a standard material as a function of energy. So these were collected at two different energies, and you can see we have a reasonably good angular resolution compared to the home conventional sources. As I mentioned, we have a Pilatus area detectors, 300K, and the pixel size at that case 172 micron for every pixel, and we have a full of 8.4 centimeter. So this is the direction where we integrate and we collect one frame of diffraction. So one frame is about 6.4 degrees. So we can stay at a specific angle in order to see the changes in one of the peaks with time, if we are interested just in a very, very quick time to follow up the transformation, or we can collect the full pattern, just every frame 5-6 degrees, we can decide it, and the overall time of the experiment is quite short, in seconds and sometimes in minutes. At the beamline, this is the conditions that you can also visit the website for the beamline, and we still work in the powder samples in capillaries. Recently, we have also added a possibility to make flat samples to work in reflection. We have also gas blowers that we can ramp the temperature up to 1000 Celsius degree, and we can spin the sample in transmission mode in capillaries. We have also the database and the match software. We can assist users, as Andrea mentioned, that mostly of our users, they are either the first time to come to the synchrotron, or they are still learning how to use the synchrotron. And in this case, we assist in many of the proposals in terms of analysis and performing the experiments. So recently, we also found the huge need to make automation for the sample change, because every time we need to change, every time we need to change the sample, we have to make a process and steps for opening the hatches, the lid hatches, and putting the sample manually and aligning the samples. And we return it back again to the control room, and which actually is a huge time loss in this case. So we bought a robot, and we currently making some tests and some uses before real installation inside the end station. These are two articles for the beamline. For more details, if someone is interested, he will find the more technical details for the beamlines, or he can also contact me in case. There are lots of applications that we can do at the beamline and material science beamline for X-ray diffraction. So X-ray diffraction, actually, it's one of the basic technique in every synchrotron, and even in universities, in research centers. You can do phase matching if you don't know the phases inside the sample. Or we could do also quantitative phase analysis if you would like to know how much phases for how much concentration, weight concentration for every phase inside the sample. We can do also microstructure relying on the analysis for the shape of the peaks itself. We could also do the in situ X-ray diffraction for many cases. If you prepare one of the sample, you're also interested in the stability of this sample. You don't need to use the sample at unstable temperature. So many users actually come to you to follow up the temperature transformation for their sample in order to see the range that we can use these samples. So in terms of energy application, pharmaceutical applications, whatever kind of application, as long as we have a crystalline material, we can apply the X-ray diffraction technique for these materials. So now it's time to give some just selected examples for some experiment already done at the beamline. And I will start with the first experiment actually was done at the beamline. Also, as mentioned by Andrea, we started the beamline in quite difficult time, pandemic period, that we couldn't host physically users here, except Jordanian users. So we started with a group from Royal Scientific Society in Jordan, and they were working in metal oxide frameworks, which is quite interesting for many users and many researchers nowadays, because it's combined between metals and organic materials, and it has advantage of some cavities or some porous voids inside the structure, which can be attractive for some gases to absorb carbon dioxide, for example, for environmental applications, or can absorb also H2O from environment for some applications that to gain and to harvest water from air. So the first example was to capture carbon dioxide for these metal oxide frameworks. And it came that this is the first picture collected at the beamline, and you see everyone is wearing a mask. It was a hard time, and it was interesting also for us to make this beam time into operation in this hard time. So it was a challenge, and it was a successful challenge, actually, I would say. So the same group, actually, they worked also in the stability for these samples they were interested in order to see the transformation as a function of temperature. And this is the second paper. They actually published a couple of papers in high impact factor journals for same material, for same group of materials, I would say. This is the gas blower, and you can just add the capillary on the top of the gas blower, and it's quite simple. Just need a good alignment between the sample and the gas blower. So the same group also, they are a very active group in Jordan, actually, and they are also working in metal oxide framework in terms of absorption, desorption for H2O from air. And this is an example that during the morning that this material is capturing and harvesting the H2O molecules from air. And in the evening, or just when you heat it up, or you just leave the sun goes through the sample, it will evaporate this H2O from their structure, and it can be condensated in order to be collected later on. And this is quite an important project for this group, because Jordan is one of the known country for very limited resources for water, and they are working in this extensively in this kind of materials and research. The second example I would like also to mention, a group from United Arab Emirates. They are working in some planets. They are capable to condensate water. They are actually grown in a very saline soils, and they are capable to condensate water from the soil. And they are interested to study the effect of the soil on the concentration of the salts that is made by the planet itself. And sometimes they are very low concentration. So here they use the advantage of the synchrotron of the beamline, of high resolution beamline, and also they are the high flux. So in a very short time, you can collect the high resolution diffraction pattern, and in this case, you can make a quantitative analysis even for very, very limited and very low concentrations of salts inside. And this was one of the successful actually experiments. They were testing the beamline, whether it was useful for them to apply for a proposal or not. So in some cases also we arrange with promising users, if they are not sure that their experiment or their samples can make a real good experiments, or they can gain good results from the experiment or not, we can arrange this. So just send the sample, and we can run this quick experiment. And from the preliminary experiments, we can decide whether it's worth nothing to continue or not. So the last, one of the last examples, just to stick to the time, it was about the hydrogen storage application. So one of the group from Turkey, they were interested in working in hydrogen storage, and hydrogen storage is one of the research challenges. Actually, hydrogen is one of the best element in order to use for energy, as a very clean energy, but it has a very limited or very drawback. In terms of research, it's a gas. So in terms of energy density, you cannot compare hydrogen as an energy material to gasoline or to petroleum, because they are liquid and they are producing more energy. One of the solutions is to store hydrogen in solid material in order to desorb it whenever you need it. So you just use temperatures in order to remove hydrogen from the structure. So this group actually used zeolite materials, and by X-ray diffraction you can analyze and you can understand how the structure has the effect on the desorption properties, and also how this will affect on the amount of hydrogen that you can store inside the structure. So they reach it to the 20 gram per liter at 50 bar at room temperature. So this was the results, the final results they obtained from their samples. And yes, as I mentioned, X-ray is a very good technique to study and to solve the structure. In this case, to see how it affects on the energy application for hydrogen storage materials. So this was the articles they published out of this beam time, and for more information, you could also visit this beamline or have a look visit this article and get more information. So the last kind of materials I will mention in my presentation, they are also attractive for its kind of fashion for many users now. It's titanium oxide, and it has advantages of using in photovoltaic applications, and actually also for batteries, for some biological and drug delivery applications. So the group from Egypt, actually, they work in the one of the doped materials, titanium oxide, and they can, by using X-rays, they can actually know where are the doped atoms went inside the structure, and how this will be linked to the physical properties for these samples. So they already published an article out of this beamline, and also you can follow up the effect of the crystal size of these samples as a pure titanium oxide on their photovoltaic efficiencies. And this is one of the diffraction pattern for nanomaterial, for nano titanium oxide, pure titanium oxide. Even if you tune slightly the crystal structure, especially at low, very small crystal structure, you will get a very different physical properties for titanium oxide. So you could also follow up the effect of temperature. So if you heat up these samples, you can just track the crystal size distribution, how it goes with temperature, from which you can understand the range that you are interested to work in, so the stable range for these kind of materials before changing completely the microstructure and going to the very large crystal. And this is one of the in situ X-ray diffraction samples was done at the beamline. Mostly of these results actually under analysis so far, but they are very promising results. So just as a conclusion, at the beamline, I hope I really gave you the general description for the recent status for the beamline. It became operational recently, and it started to make a really good science and good high impact research. And I would say enter to the club for X-ray diffraction. It's not, of course, sometimes it's not, you cannot compare with the other synchrotrons, but at least in our region, it's capable to make mostly of the experiments we need here. And of course, there are many resources and many contributors enter to need acknowledgement and enter and assisted during the installation for the beamline, for the MS beamline. It wasn't easy, but it was also a challenge. So it was nice also to start as a donated components and to see how we can use this in the best condition and the best way. And here is the inauguration for the beamline. So with the Swiss, as a Swiss light source gave us this. This is a Swiss ambassador and the UNESCO ambassador with the general director for Sesame. And this is a group photo for the installation group in Sesame. And you can imagine this is mostly of the group in Sesame, and we are very, very limited human resources, but apart from this, we actually can do a good job. And also diamond synchrotron, because they are donated to us, the refurbished, not refurbished, an old diffractometer, and we refurbished it to use it in the proper way for powder diffraction. And of course, Dictor's company, because they donated a detector, and without the detector, we couldn't do any research and any X-ray diffraction experiment. And thank you for your attention.
Thank you so much, Mahmoud.
Thank you.
So again, if there's any question, please drop it in the chat menu, chat window. And Mahmoud, please also, maybe you can drop your email. So if anyone has a question, can ask you later. Now we move to the next talk in our program, which is given by also my colleague, Dr. Mustafa Gencho. Mustafa joined, okay, first of all, of course, he got his PhD in 2011 in chemistry in Turkey, and he joined Sesame recently. He's the beamline scientist responsible of the first soft X-ray beamline of Sesame named HAZEP, which is Helmholtz Sesame beamline. And Mustafa will give us also a brief about this beamline in 30 minutes. You here, Mustafa? Are you here? I don't see Mustafa. Or... No, I don't see him.
He might be using the link with my name on it.
Oh, really?
I think that's the one he was having trouble signing on.
I think he has troubles to
oh, here he is.
Here. Oh, perfect.
All right.
Okay, Mustafa, can you please start?
Yeah, cool.
Yes, can you go to the full screen mode? No, we can't hear you. So no, we can't hear you.
Me?
Yes, now yes.
Yes.
Now yes, perfect.
Sorry.
No
Thank you for a nice introduction. Good evening, everyone.
Mustafa, can you please go to the full screen? And you have
Yes.
30 minutes also.
Yes.
Thank you. Thank you.
Okay. Could you hear me now?
Yes,
okay.
we hear you. We hear you.
Okay. Thank you. Sorry for this problem. Good evening, everyone. My name is Mustafa Fatih Genişel. As I am the beamline scientist of HAZEP. In this presentation, I'll mention about the HAZEP, the first soft X-ray beamline at Sesame, and the research opportunities it brought to Sesame. So first of all, I want to give an outline of my presentation. As I mentioned before, HAZEP is the first soft X-ray beamline in Sesame. So what is soft X-ray? And the interaction of soft X-ray with the matter. I will mention about interaction of soft X-ray and matter, and the analyze techniques which is used in soft X-ray using soft X-ray. Then I'll give information about HAZEP project. After that, I'll give information about what is HAZEP beamline, its properties, capabilities, and at the end of my speech, I'll give a very brief information about our sister project, TextPass. First of all, I know that most of you know this electromagnetic spectrum, and what is that? And this electromagnetic spectrum is divided by visible light into two. One is lower energies and higher energies. And in each region has a different interaction with the materials. So when we, because of our speech, when we focused on the higher energy range, we will see that the photons in that region is mainly related with the core shell electrons. And what we call, what is soft X-rays? Soft X-rays are the photons with energies between 200 electron volt to 2000 electron volts. They are not very strict. These numbers are not strict, but these are just accepted numbers. And what happened when a photon touched the material, and what are spectroscopy is about that actions. When a photon come to our material, it will either transmit it by lower intensities sometimes, or it will reflect it. This part is not the scope of that presentation. Or it will be absorbed. When absorption occurs, there are some complex procedure happens inside the matter, and it will either emit a photon, or if it is possible, if the energy is suitable, it will emit electrons. So let's look at why X-ray is related with core shell electrons. You can see a schematic representation of the shells and molecular orbitals, and in here, physics call these orbitals as name these orbitals as conduction bands, but for chems it is LUMO, or valence band, or for chems it's HOMO. And core shells are the shells which are fully occupied by the atoms, and mainly these orbitals, these electrons are mainly related to one atom. They are bound mainly on one atom. So any change in here also affect the energies, or the energies of these photons, these electrons, sorry. So let's look at the absorption of X-ray. When we send an X-ray with an energy is lower than these core shell electrons, it will transmit it. But when we increase and there is no absorption, the absorption is low. And when it reaches a certain point, which can be absorbed, or when electron absorbed, there is a state in the upper part, it will absorbed by our material, and our absorption increase. When we increase the energy with a certain, accept certain levels, it will not absorb very well, and it gives us this kind of figure, spectroscope figure in our measurements. We call these are edges of these well-known numbers. These are very well known because they are tabulated for the atoms. These edges are very well known, as I mentioned. These are when you look at the 200 and 2000 EV and soft X-ray. The K shell of these atoms can absorb the photons in soft X-ray, or L shell of these atoms can absorb the soft X-ray. But as you see in here, carbon, nitrogen, oxygen, or argon, these are in the air. So soft X-rays needs beamlines, needs vacuum. It requires vacuum. When we look at the other atoms, almost all periodic table can be analyzed by a soft X-ray. So what happens, and what are the X-ray absorption related techniques? Again, when a photon comes to our material, it will transmit it, but intensity change in this case, but it's common in hard X-ray beamlines, but it's not common in soft X-ray techniques, because soft X-ray is very sensitive to material, and so it interacts with the material and so it needs 2 thin samples, and it's not used too much. But what happened after complex procedures? It will emit photon, which is fluorescence. Most it is lower energy than the incoming photon. We call these techniques XRF-related techniques, and either it will emit electrons, and we can either look at the number of the emitted electrons, or we can make a kinetic energy measurement of these electrons. We call these electrons, we call these techniques is X-ray photoelectron techniques. And it is related to text-based. I'll mention these techniques at the end of my presentation. Also, if our material is conductive, because of that emitted electrons, and positively charged is accumulated on the surface, if we ground our sample, and electron current can be measured, and drain, we call this drain current measurement, and we can understand the photon is absorbed by our material. Let's look at the absorption of X-ray and total electron yield. When we send a photon and up to certain point, it will not absorb, and the drain current is 0. And after it reach not 0, very low, and when after photon is absorbed by our material, our atoms, it will start to, it will emit, an electron will be emitted from our sample. And because of that, we will start to read drain current, and it continues like that. So we will understand that when our X-ray is absorbed. But in this case, our material have to be electrically conductive. If it is not non-conductive insulator, it will not work. On the other hand, when we look at the fluorescence part, again, when we send a photon to our sample, it will give this kind of absorption in each level. When these photons absorbed, it will emit electron from these core shells, and these empty orbitals will be occupied by the electrons which are dropped from the other orbits, and they will sometimes, not always, sometimes give photons. They emit photons, and by looking at that photons, we can understand these incoming photons are absorbed by our material. By looking at the energies, we can make qualitative energies, and intensities, we can make quantitative energy analysis. Let's look at what is HACCP project. But HACCP project is actually the abbreviation of Helmholtz and Sesame beamline. Helmholtz-Sesame beamline. The project period is 4 year, and founded by Helmholtz Association in German, and it's a German institution. And 5 German institutions are in that project, and their partner is Sesame. And let's look at the plan view of HACCP and its sister project TextPass. Both of these projects use same undulator as a source, and they will use same PGM as an energy dispersion element. And we use an M3. We use 2 M3. With that M3, we can either direct our photons to the left or to the right. And we call this beamline, orange one is as HACCP, and it sends the photons to the HACCP end station. If we change the mirror in here, and it will direct the beamline photons to the right beamline, and at the end of that beamline, TextPass end station will be placed. So let's look at our photon source. It is an undulator. It is placed in the stage section between cell 10 and cell 11. It's Apple II type undulator. Its minimum energy is 70 eV, and it can produce either linearly or circularly polarized light. And its period length is 56 millimeter, and there are 30 periods of magnets. You can see the undulator. It's 9 ton weight, and it is between cell 10 is in here and between cell 11. So what are the properties of HESEP beamline? HESEP beamline, the theoretical energy resolution is better than 4000 at 400 EV, and it has two grating mirror, 400 and 1020 groove millimeters, and it can work linear or circular polarized light, and photon energy is between the working energy is between 90 and 1800 electron volt, and it will cover almost whole periodic table except hydrogen, helium, and lithium. And spot size at the end will be 150 to 250 micrometers square meter. And we are planning to use an optical capillary. If we use this optical capillary, it will be 20 to 20 square micrometer. Let's look at the end station of HESEP end station. It has a manipulator. Manipulator is motorized, so we can make 2D mapping with the resolution 1 micrometer. Here is our analyzed chamber and vacuum section, vacuum equipment of that chamber. And when we look at close look at the chamber, here is our chamber. It's connected to a load lock system. With load lock system, without venting our chamber to the air, we load our samples on the receptacle part, and this is another view of chamber. This is it is a photon path, and there's a fluorescence detector in here. Let's look at the load lock and magnetic transfer arm. This is our magnetic transfer arm. This is load lock, and you can see the loaded the transformer arm is loaded with sample holder. With that, with the help of that load lock, we can we can load our samples less than an hour. So what are the properties of end station? It has an fluorescence detector, so it can make fluorescence measurements, and it has an it has a picometer is connected to our manipulator, and we can collect data we can cool the manipulator with liquid nitrogen, and we can heat the sample. And now we are working on magnetic stage. If we could achieve this, we can make XMCD measurements, and it has a motorized sample holder, as I mentioned before, for 2D mapping. And the important part is the unique part is a differential pumping system. So you can make measurements at low vacuum environment under helium atmosphere for vacuum sensitive samples, especially for historical samples, because the owner of the historical samples, especially museums, don't want to put their samples in the ultra high vacuum environment. So with help of this system, differential pumping system, we can make we can collect data at a low vacuum environment, or we can also control the atmosphere. We can make measurements at controlled atmospheres. So let's look at the sample holder. You can see the picture of a sample holder and to the drawing. It has an liquid. In here, we fill this area with liquid nitrogen, and this stage is for low temperature stage, and this stage is for E-beam heater, and we are planning to make it a magnetic measurement stage. And here is our high temperature stage. It has an bottom heater at the bottom, so we can heat up our sample up to 800 degrees. And this is a photodiode in here for diagnostic. So we can make the we can look at the profile, beam profile. We can collect beam profile from that photodiode. The sample holder is a standard sample holder, and we can put the maximum area is 14 to 14 square millimeter. I want to mention what is differential pumping. What I mean when I say that differential pumping. Here is a sketch. This is our HACCP chamber. It has pumping unit and it has a gas inlet system, and there's a coupler in here. The pinhole in here is about micrometer level, and we can fill this area with helium. And so photon beam can pass through this capillary and hit our sample. So fluorescence fluorescence detector can approach our sample. With the help of this system, we can make measurements at high pressures. And there is a pumping unit in here. If the gas can go through this area, we will pump it out without disturbing the other side of the beamline. Because there is a valve in here. This valve allow the X-ray can pass penetration of X-ray, but it stops the gas molecules. Here, I give every brief information about the commissioning of HACCP. We could first beam out of the tunnel in January, in June. And here is the harmonics of the undulator. This is the you can see the harmonics. It's not the continuous, and you can see each harmonics in here. And this is the graph version of that data. In the, our peaks are at different energies. Here is where our commissioning is still continue. This is the nitrogen gas peaks in ionization chamber, and we can see the vibrational state of the nitrogen molecules. Forthcoming steps, we are planning to finish the alignment and the calibration of the photon beam, and we will finish the tests on the experimental chamber, and we will start to use, make measurement with friendly users, and we are planning to collect proposals in the March 2023. I just give a brief information about TechSpecs projects. Again, it is in the same, it will use same undulator and PGM, but its analyzed chamber has an kinetic energy analyzer. So you can make XPS, UPS, and Auger electron spectroscopy techniques, and it has an benchtop UV and X-ray sources, and you can make a low energy ion scattering and ion scattering spectrometry, and has a variable temperature sample manipulator, and you can it can work under either liquid helium or nitrogen cooling temperatures. It will have an ion gun for depth profiling, and it has an electron float gun. So what is XPS? When I mentioned previously about X-ray absorption and related techniques, XPS is when electron is emitted by the photon. When you make the you measure the kinetic energy of the emitted electron, by this measurements you can obtain the binding energy of the electron to the material, so you can make decision of the chemical environment of your material. So TechSpecs has different sample preparation chambers. Without opening the air, you can make you can prepare your samples. It has e-beam metal evaporators, gas dosers, atomic hydrogen cracker, QCM, RGA, and atomic layer deposition valves. I want to thank to my HACCP project team and my colleagues in Sesame. And I want to thank all of you for your patience and attention.
Thank you so much, Mustafa, for your presentation, also keeping the time. Again, if there are any questions to Mustafa, please drop it in the chat. And I saw that already Mustafa has also dropped his email address if anyone is interested to contact him later on. Now we end this session and also the program of today with my colleague, Dr. Gianluca Iori. Gianluca is graduated He got his master's degree in mechanical engineering from the University of Bologna in Italy. Then he got his PhD in biomechanics in Germany. His research focuses on imaging, numerical simulation, and also on the mechanics of nature's materials. He also joined us recently in January 2020 at Sesame, and he's coordinating the design and the construction of the BEATS beamline, which is the beamline for X-ray tomography at Sesame. Please, Gianluca, the floor is yours for 30 minutes.
Thank you very much, Jihan, and thanks to the attendees who stayed until the very last presentation. Can you please confirm that you hear me and see my full screen?
Yes, all is perfect.
Thank you. So my name is Gianluca. The email is here, and I also already dropped it in the chat. I'm going to present the project for a beamline for X-ray CT, so computed tomography at Sesame, which is a Horizon 2020 European funded project coordinated by the ESRF and developed in collaboration with the 9 facilities in Europe and the Middle East, which I have listed here on the bottom. The project started in 2018, and as you will see, we hope is about to deliver the beamline. First, briefly, an outlook of my talk. I have a first part on the BEATS beamline. So what is X-ray CT? Comparison with lab CT, and the actual status, project status in terms of beamline installation. And then I have a second part on scientific opportunities that will open up starting from next year. Luckily, I don't have to go through the theory of X-ray CT, since we had marvelous talks in the afternoon covering full field X-ray imaging. So I'll just recap that computed tomography is an extension of X-ray radiography. The first radiograph from 1895 is here on the left. The first CT scan introduced in a hospital in the UK in 1971 is here on the right. What this device is doing is it creates images of the interior of the body, like of the human head, in this case, by rotating a system of X-ray source and detector around the body itself. At the synchrotron, life is quite different, since we cannot rotate our X-ray source. What we do, we need a larger experimental station. This is a photo from the Swiss Light source. The X-ray is coming in from the left. We have a sample here in the center, and what we do is we rotate the sample in front of the microscope and collect projection images under 180 degrees of rotation. These projections are then reconstructed by a computer to obtain a 3D rendering, a 3D volume of the sample under study. And I hope I will be able to show you enough examples later of what can be done in terms of image resolution and sample size and the variety of samples that this can be applied to. But first of all, a quick comparison with what you find in the lab. So lab X-ray CT is a device that typically works with a polychromatic source. Since the photons are few, you don't want to throw them away. You use all the spectrum, and generally works in a cone beam geometry like this one, which means that by putting the detector further away, you can enlarge the magnification, or by putting the sample away from the source, you can work with larger objects, larger sample sizes. Typical scan times here are minutes up to, for large objects, several hours. At the synchrotron, on the other hand, we can generally target smaller samples, since the setup is a parallel beam geometry setup, like here in the picture. Therefore, generally, the field of view is relatively smaller. but there are some characteristics that are unique. First of all, the flux is higher by several orders of magnitude. This means that we can throw away a lot of photons using a monochromator, improving greatly the sensitivity and limiting the artifacts in the scan. Today, we also heard about spatial coherence, beam coherence, and this opens the door to phase contrast, which is only available when the beam has a certain degree of coherence. And then another factor in synchrotron X-ray CT is that the greater flux allows to reduce scan time drastically. So from minutes up to seconds or even below. And this, again, enables a completely new technique, which is time-resolved CT or 4D CT, which can generally be targeted or employed only at the synchrotron. Now, going to the project here at Sesame, this is a 3D sketch of the beamline we are installing. Some characteristics, it's a long beam line, 45 meters, to improve the phase contrast, the spatial coherence of the beam at the sample position. We need to work with a broad energy range to penetrate and image also large objects and dense samples. We have a combination of detectors I'll show you to cover pixel sizes between 0.65 micron and 13. And a beam size at the sample position up to 72 millimeter horizontally, which allows us to scan already samples of a significant size. We can work in two modalities. We can work either with a filtered white beam, so just letting the complete spectrum through and scanning with as high a photon flux as possible, or using a monochromator for applications requiring more sensitivity. This is our source. It was designed by Alba. It's a very compact one. This is the day we received it at Sesame. It has a peak magnetic field of 2.92 Tesla. You see here the peak and the two straightening poles on the side. And this gives us a broad X-ray spectrum that we have compared here with simulations to the ones of the beamlines for tomography at the Swiss light source, at Cara in Karlsruhe, or at the Italian beamline CIRMAP. So you see we are there in terms of energy spectrum and intensity. This is how it looks when it's in place. Our engineers and physicists coordinated the installation of the source in last August. This is the day we put the source in. You see here the jaws of the wiggler are open to place the vacuum chamber where electrons are running through. And here is it after alignment and finishing the installation with the corrector coils back in place. And the minimum gap here in between, you don't see there is a vacuum chamber for our electron beam. This is a front end also installed during the August-September period. The main components in this front end are beam shaping and attenuators to change by filtering the beam the minimum energies, reducing the flux to protect components, and filtering high energies. This is our mono. The device has arrived, is at Sesame, and will actually be positioned in the optical hutch next week. It's a large device. You need long mirrors to reflect a broad beam with low grazing incidence. It's a double multi-layer monochromator. And here you see two snapshots from the operation of it, covering a range between 10 keV and 50 keV. These are some pictures from the installation period and current status of the installation. I already mentioned that everything inside the Sesame storage ring is in place and in vacuum. Our infrastructure and shielding hutches are in place, ready to receive the rest of the equipment. You see a picture here on the bottom right. In the center, there is the first of our 2 detectors, which is also born in a plane in the next days. Where we are now, it's optics and experimental station installation between October and January to start hopefully commissioning in January next year. And here's a group photo we took in September after installing the front end. This is the beamline front end with a group of colleagues from the SRF and Solaris France and Poland respectively that came to support us during the installation task. Now, as a user, what you, or hopefully you, will find at the beamline is this experimental station where we have a granite stage that was designed and optimized in a collaboration with the SRF and the University of Johannesburg to reduce vibration by increasing the first eigenfrequency mode of the strut. On this big granite, we will have a sample manipulator, which is a donation from the Swiss Light Source, and a detector manipulator where we can swap between 2 detectors. The detectors can cover a whole range of image magnification between 0.5 and 10x. This means pixel sizes between 13 micron and down to less than 1 micron. And they are indirect detectors with the scintillator lenses, microscopy lenses, and scientific CMOS cameras, as you see here in this diagram. And this is the plot of our beam available at the sample with different magnifications indicated. Now, going to the second part of my talk, I will try to cover all the scientific opportunities that will open once we become once we go online. The scientific case covers 4 main areas of research, which are archaeology and cultural heritage, health, biology and food, material science and engineering, as well as agriculture and environment. And I will try to give some examples from each track, from each field. But first of all, like starting with cultural heritage and archaeology, the first aspect here is that the range of artifacts, materials, and samples that we can scan is huge, in the sense that we can target pottery and ceramics, glass, textile, wood, or ancient manuscript, but also in complete plant and animal remains, fossils, of course, and in terms of artifacts, bone, antler, and teeth. We can also work with complete statues and ornaments. So from these slides, you see already that the range of sample size and characteristics can really vary a lot, from thin and tiny samples like these beads or papyri, up to complete or entire manufacts like statues or vases. What we are envisioning, therefore, is already an upgrade of our experimental station, and this is a call for tender which is going out now to expand our sample manipulator with a second station for larger samples. So this, hopefully in 2024, will expand our possibilities from samples from 5 kilograms up to 25 kg, and increase, since the manipulator is independent from our granite table, will increase the propagation distance between the object, which is placed up here, and the detector lens from 1 meter, like in this case, up to 6 meters. And this is important for phase contrast applications. Now let's look at a couple of key studies from cultural heritage and archaeology. This is an example of material identification. These are ancient beads from the Paleolithic, and it was not clear when these objects were found what type of materials they were made of. It could be ivory, it could be also antler or bone. the unique aspect of X-ray CT here is that one can look at the interior microstructure of these objects without completely touching or damaging the manufacture. So for rare and unique samples, this is a very important aspect. In this case, this was mammoth ivory, and it was discovered using a combination of absorption CT at different pixel sizes from 0.4 up to 3.5 microns. Another example comes from also from archaeology. This is a sample called the Lonche canine. It's a tooth sample from the Neolithic, where again a combination of laboratory and synchrotron CT was used. So first of all, lab CT at low resolution showed cracks and damage in the tooth, and an overlaying layer of material which was not in the beginning identified. Phase contrast CT at the synchrotron was key to reveal the wear pattern and the crack pattern in the tooth. So once they saw this, researchers understood that there was something going on with this tooth, and they started analyzing the layer covering the tooth, and using, first of all, FTIR, revealing the composition of the material, which was beeswax. So this indicated that it could be a filling material and could have been applied already during the life of the subject. And this was confirmed using radiocarbon dating. So this study, in fact, demonstrated the first palliative treatment in dentistry or dental filling in a human from the Neolithic. Another track in cultural heritage that I would like to cover is glass scanning. And these are images. This is a project that we are running together with researchers from the Italian Institute of Technology in Venice, in Italy, and the Italian synchrotron. Here we are applying some of the data processing techniques that will be available at BEATS through beam time that we had at a partner facility like Electra. So this is a study on Roman glass samples, also unique samples of different origin, so different manufacturing processes. Like these two are objects from the bottom of jars, and this was an ink container. Some others come from ornaments or glasses, or they are called polychrome samples. Here, synchrotron CT, X-ray CT, allows to understand different aspects of, first of all, manufacturing, in terms of which tool was used, and this can indicate the technological level of the society, of the group who produced these samples. The shaping method can be deduced from the internal and external shape of the objects. But also polychrome decorations can be tracked, since these polychrome inclusions are generally produced with opacifiers, which are generally made of mixing glass with metals such as lead. Therefore, they have different absorption in X-ray imaging, and can be reconstructed. Therefore, their internal structure and distribution can be reconstructed in 3D. Finally, and I will show more on this, the degradation of glass can be studied. And this was particularly the target or the objective of this work with the Italian researchers. So this is a cracked sample, and the idea here was to understand how deep these cracks are running through the sample and their internal architecture. So this is a preliminary scan done with a laboratory CT, and you see that you can already identify a crack pattern but cracks are very difficult to distinguish from the bulk glass as well as from the soil, which is filling the cracks. Don't forget that these samples were under earth for about 2,200 years. So when we zoomed at part of these samples with phase contrast CT at the synchrotron, you see this is already a factor 10 from 20 micron pixel size to 2 micron pixel size. We got a perfect reconstruction of one of the edges of this sample where we can study in 3D the crack morphology, but we can also separate the filling, so the soil, different components in the soil from the crack itself. So we get a perfect characterization of the crack depth and size, as well as of the complete sample porosity. We did more on this sample, which presented a strange scratch on the bottom. This is an ink jar. And this is, again, a laboratory CT scan. This is a zoom of an area scanned with the synchrotron CT. And here, this is called a pit. The objective here was to characterize what the origin from this pit filling, if it was coming from the soil or if it's part of the glass degradation itself. And again, this is a unique object, so you want to do it with a completely non-destructive technique, and you really place the sample in the X-ray beam, and you don't touch, you don't cut, you would need no sample preparation compared with techniques such as SEM, TEM, or whatever. When you take this pit at really extreme resolution, so 1 micron pixel size, you see that it is a layered structure. And between the different layers of corrosion or deposit, there are minerals forming in. So this study induced further research and instructed a further proposal using XRD, so X-ray diffraction, to characterize the origin of these minerals. What you can do with the TOMO, so with the 3D tomography, is to look at this pit in 3 dimensions, characterize its morphology and therefore its history, but also look at the distribution of voids and mineral droplets. So the history of pit formation here reveals characteristics of the surrounding soil and the time span that elapsed during the formation of these layered structures. And finally, the ultimate goal is to really understand damage and degradation processes in ancient glass, to stop them and drive new techniques for restoration and conservation. So these are some of the latest 3D renderings that we obtained on this sample. Now, to move forward from cultural heritage and archaeology, I have some examples from health and biology. Again, here the type of samples is broad. We have characterization of dental and bone samples, such as implants. In this case, this is a dental implant, whereas here on the left, this is a video from a 3D rendering we obtained of a bone implant. In the center, there is a mineralized algae sample from the Red Sea. This is a mineralized structure that is organized in 3D to resist the stresses and the stresses from the water current on the seabed. One can study the internal microstructure of food, such as green beans in this case, or the morphology of objects or of insects from fossils or current species. From material science and engineering, I want to show 3 examples. The examples on the top belongs to light materials and alloys. These are stainless steel struts that are obtained by casting. So gray cast iron steel foams that are particularly important because they are lightweight and they absorb energy during shock. So they are very interesting for aerospace engineering. You can see that they contain defects, and these defects will drive crack formation and stress accumulation during their mechanical life. From left to right, you see a high resolution scan of a single strut. You see the image moving here is a 3D render of a complete foam. And from these 3D images, you can inform 3D finite element models such that goes through a meshing procedure, like here in the center, to really understand also the put the sample under stress virtually and understand their mechanical compliance or their mechanical response. On the bottom, there is an image from concrete research. This is a concrete mixed with recycled grinded tire rubber. Whereas on the bottom left, this is a material science application in regenerative therapies. This is a root canal therapy of a damaged tooth. The left image is from a lab CT. The right image is from synchrotron CT. And what you see in the center is a fiberglass post, which is a post supporting the new crown, which is inserted in the tooth during the therapy. It turns out that a lot of failure rate or infection in this therapy is due to or driven by residual air and a residual space that remains during the procedure between the tooth, the new composite making the new crown, and the glue which is placed between the fiber post and the other materials. And here you see really how these small voids are invisible to laboratory CT and become only visible and can be characterized in terms of size, area, and shape only using phase contrast CT at the synchrotron. For material science, one track we're following is the construction of a sample furnace. This is an induction heating system that can reach 1800 degrees and was studied and optimized again by a master student we hosted between Sesame, the SRF, and coming from the University of Johannesburg. And here you see details of the finite element simulations that drove the optimization of the crucible design and of the whole furnace itself. This is a device that we will fabricate next year. Finally, I have just some examples from agriculture and cultural heritage. On the right, there is, agriculture and environmental sciences. On the right, there is a scan of soil where we can distinguish and isolate and then compute characteristics of the different phases. So the whole soil here is on the top, and then pores and organic phases are isolated and quantified on the bottom. In the center, there is an image comparing soil tillage techniques with on the right and zero-tilled soil on the left. These are completely different or two different agricultural strategies showing that reducing soil tillage in an environment, this was in the UK, I believe, helped in terms of soil stability, reducing the soil erosion and compaction as well. Finally, on the bottom left, there is an example from rock science. This is a 3D characterization of a sandstone core, where different colors are the different results of a permeability simulation. So properties such as permeability and percolation can be derived from a 3D scan of this rock. And with this, I think I finished my talk. I have once again here the links to our Twitter and webpage, as well as my email, in case you want to ask questions or know more about the beamline.
Thank you so much, Gianluca. And again, I saw that Gianluca already dropped his email in the chat window. Please contact him in case of any question or interest. So this stage, I thank you so much for your persistence to this time with us, even with this delay. And we hope that we managed to present our facility in a beneficial way to all of you. We look forward to cooperating with all of you, attending of our beamlines, and I really hope to see you soon at Sesame until we manage at a certain point of time to meet in Africa. So thank you so much, and I leave it to Philippe. Thank you so much.
All right. Thank you very much. Thank you very much. Today is a very long day, and I can believe that the presentations, they are very standard, and I think majority of us here in Africa, they listen now. We know that at least there are some things we need to do. So I will tell it, and I will believe that this presentation will enable a lot of people to contact different beamline, and I generally know that once they put at African License Conference, they should know that, okay, it's the product of this conference. So to our colleagues, I think we are done for today, and I hope to see everyone tomorrow. All right. Thank you very much. Let us open our something. I just try to wave and say bye-bye.
Thank you.
We should mention that the director of Sesame is giving a talk on Friday.
Yeah.
Friday. Mm-hmm. And so if you have more questions about Sesame, you can ask them then, or in the chat or the emails. And also these presentations, once they're clipped and cropped, will be on somebody's website, I'm sure. Thanks. Ours, at least. So, all right. Thanks, everyone.
Thank you.
All right.
Bye-bye.
Bye-bye.
Bye-bye. Bye. Thank you.
Wow. Beautiful.
Hello. Trevor, are you still there?